Hello and welcome to another coding session. How about that? Bet you didn't expect that shit to happen. So today is what? Today, if I remember correctly, is Thursday. And today I decided to learn. Actually, I already learned some stuff about LRU caches. I always wanted to learn about LRU caches, but I didn't really have an opportunity. So yeah, for the past 2 days, I was just playing with the idea of LRU cache. And today I wanted to do like a summary stream of what I discovered and also maybe teach you something and maybe also answer some questions and stuff like that. So today we're going to take a look at a simple, very simple problem that could be solved with LRU caches, but really it would be better not to solve it with LRU caches. So the first thing I noticed about LRU caches is a shit ton of different misconceptions, right? Right. So people kind of assume that LRU caches is about really like optimizing the speed of the program, which is true to some extent, right? Which is true to some extent. But what I discovered, it's more about optimizing the space of the program, like how much memory it consumes while trying to maintain a reasonable speed. That's what it's all about. So, and yeah, to understand what the hell is going on, we need to understand what is a cache, right? So what the hell is a cache? Right. So a cache is basically the idea that you have an expensive operation, right? You have an expensive operation and you don't want to perform that expensive operation way too often, right? So you perform it once, you save the result of that operation to some sort of a memory, right? And next time you need to perform the operation on that specific input, you just take the result from the cache without performing the expensive operation. That's what we call a cache, right? I think so. Like, I don't have a computer science education, so I don't know what I'm talking about, but maybe that's what we call cache. Right, so this is what we call cache in general. So what is LRU cache? Right, so LRU stands for least recently used. That's what it stands for, least recently used. And what that means, it's a name of eviction policy. Right, having a cache is cool and all, but for instance, if you have a browser, right? If you have a browser and you cache in the web pages, right? So querying the web page is an expensive operation. So you want to cache the web page, so the next time the browser tries to query that page, you don't load everything, you only take it from the cache. But can you cache the whole internet? Right. So to cache the whole internet, you need to have as many computers as there is in the internet. I don't know. Maybe it's not true. Like, I don't know. I need to perform like a proper like back of the napkin calculations to do that. Yeah. So you definitely have a limited amount of space. Right. So, and for instance, let's imagine that we allocated 10, like maybe, okay, 2 gigabytes of cache specifically for the browser, right? And we ran out of space to cache more pages, but we already see the pages that we want to cache. What do? We remove things from the cache, right? So, and the next question is, what exactly do we want to remove? Well, it would make sense to remove the things that are used the least, right? Because in the cache you may have pages that you rarely visit, so you're not that often gonna hit them in the cache. So it's better to remove them, right? We better remove them and keep the frequently used pages in the cache, so the next time you do things around, on average, it feels faster. So I suppose the first misconception is that LRU caches are all about optimizing speed. It's not necessarily true. It's trying to optimize the speed given a limited amount of space. Right, you have a limited amount of space and you do what you can with what you have. It's not really about the fastest possible solution. A fastest possible solution will probably require an infinite amount of memory or something like that. So this is quite important to keep in mind, I think. And this is the first like misconception that people have when they talk about LRU caches. At least this is what I discovered, right? So I'm not an expert in LRU caches or caching or anything like that, but that's what it feels like. right? Because quite often a fastest solution may not even involve doing any eviction from the cache, right? So yeah, that's basically what it is. I never understood why it was named LRU, even though yeah, apparently this is a problem. So what I've noticed, people use words cache and LRU interchangeably. Like, for people, there's no difference. Okay, LRU and cache is the same thing. But there's distinction. Cache is just like a general storage where you remember the result of the expensive operation, and LRU is a policy of removing things from the cache to free some space. But you don't need LRU if the amount of operations you do is very small or you have an infinite amount of memory, right? So yeah. And this is like where a lot of sort of like misunderstanding and misconceptions comes in, I think, right? People just use these two things interchangeably. It's not true. So cache is a cache and LRU is just a policy of evicting data from the cache, right? By certain criteria, and that criteria could be least recently used. I've seen it used in relation to sorted cache as well. Yeah, I guess you basically sort by how recently you use things, right? And that could be also called LRU cache or something. But anyway, so today I want you to actually go ahead and implement an LRU cache. I already implemented that cache before, right? Just to notice. But I still want to re-implement it from scratch, specifically for people who's going to be watching all of that on YouTube. Right, so I want to implement an LRU cache in pure C, right? And to do that, we need to come up with a problem that we can solve with an LRU cache, right? So the usual structure of the problem that is solved with LRU cache is as follows, I think. I'm not 100% sure, but I think the structure is the following. You have a sequence of events, or maybe a sequence of queries, right? Right. A sequence of events and sequence of queries. QN, right? So, and this is sort of like a stream of events, stream of queries. Stream of queries. And on each query, you need to have an expensive operation that you can perform, right? So we can call this, I don't know, EOP stands for expensive operation. Maybe I'm going to just do E, right? So E of query 1, E of query 2, and so on and so forth, right? And on each operation, on each query, we can decide whether to do this expensive operation or take it from the cache, right? Every time we perform this expensive operation, we put it into the cache, and next time if something similar comes in, we just return it from the cache. Right, so the toy problem I came up with is the following. Imagine that you have a file, something like Shakespeare TXT. So it's absolutely toy problem, and it's probably not the best way to actually demonstrate LRU caches. At least that's what I learned, but I cannot come up with anything better that I could implement in a reasonable amount of time. Right, so because I want to implement LRU cache from scratch to demonstrate the whole process, right? Starting from nothing, and there we have LRU cache that does things, right? So I could probably pre-implement a lot of things, and I already have some of the things pre-implemented because I'm going to be using some of the third-party libraries. But yeah, it's kind of difficult to come up with a reasonable example that you can implement in a reasonable amount of time. Right, so yeah, apparently like it's kind of difficult to demonstrate the usefulness of this entire thing, but maybe I'm just stupid, so that could be also the thing. Okay, so we have a file with words, right? So I have a special folder in here, and let's actually download this entire file in here. So I'm also going to put this file in the description for people who's watching on YouTube, just in case. Shakespeare txt, right? So this is going to be available in here if you're interested. So here's the file. Okay, and basically what we're going to do, we're going to treat each individual word in that file as an event or as a query. Right, so each individual word is basically a query. So, and what do we need to answer for each individual word? Well, we need to go through the entire document, and basically, if we see the word from this standard input, we need to spit out this word and also how many times this word was encountered in the entire document. Right, so here we have a sequence of events, words, an expensive operation going through the entire document and counting how many times the word was encountered. You can solve this problem without any LRU caches, right? So you can just pass through the entire document once, building basically statistics of each individual word, and then easily query all of that. But again, what if we have a limited amount of space? Right, so as I already mentioned at the beginning, I think LRU caches are not about implementing the fastest possible solution. It's about implementing the fast solution with the limited amount of memory. Right, with the limited amount of memory. That's what it's all about, as far as I know. And for instance, we can also do something like we can limit the amount of words we can put in our cache, right? So maybe, so we have a lot of words in here. As far as I know, there's like 3,000 in here. We can say that we're going to have 256 words. And we'll see if having that cache will actually speed things up. Right, so that's the problem. Just go through the entire file and annotate each individual word with how many times that word was encountered in the file. Right, so yeah, before we can even do that, I think we need to probably implement the ability to read the file and go through the file and count how many times a particular word was encountered there. So let's actually go ahead and do that. So it's about efficient solution. Well, no, as I said, it's not about efficient solution. Thank you so much, Lost Algorithm. Thank you so much for 19 months of tier 1 subscription. Thank you, and yeah, really appreciate it. If you want a very optimal solution, you don't really need to use LRU at all. As already mentioned, there is a lot of confusion between word cache and LRU. For some reason, people use these two words interchangeably, and I still don't understand why. But again, I know nothing about neither caches nor eviction policies. But people still use these things interchangeably. If you want the most efficient solution, you just build a hash table of the frequency of each individual word without using any LRU. You just go through the entire thing and you answer the question. Right. So if you have a limited amount of memory where you cannot fit each individual thing in there, your final solution is going to be slower. But is it going to be as slow as not having cache at all? It's not about efficient solution. It's about the trade-off. Right, you need to go fast, but you don't have enough memory to go fast. You have a limited amount of memory. What do you do in this specific situation? How can you find a balance between going fast and consuming too much memory? That's what it's all about. Maybe I don't understand what you mean by the word efficient in this specific sentence, but I don't know, maybe. I don't speak English, I'm sorry. Does anyone have any other questions, maybe, before we go and implement like reading the file and some other stuff? What are you drinking? I'm drinking tea. Okay, so let's actually go ahead and implement reading the file. So I'm gonna start by creating the file main.c, and we're gonna just include a bunch of things in here. Alright, so this is gonna be something like this. And there we go. Argcchar, argv. and let's basically try to compile the entire thing, right? So I think we need to use a build system in here. Usually I use my own build system because I find it really convenient. You can read more about this build system in here in the chat if you're watching live, or if you're watching on YouTube. I'm gonna put it in here. No build build system, right? No build system. And the idea of this build system is just like using shell scripts for building your project, but instead of shell script, you're using C itself. You're building C projects with C, right? So, and because of that, the first thing you'll have to do, you'll have to bootstrap your build system. But once you bootstrap it, you can just rebuild everything with a single command all the time, even the build system itself, right? So build system can detect that you modified the script or maybe build recipe, and it will rebuild itself. So the only thing it needs is a little bit like of a kick, right? So just bootstrap the initial thing, and the build system already starts to work itself out, and just you don't have to worry about rebuilding anything. So it's like that. It works like that. It's actually a pretty interesting idea. I'm still not sure if it's a good idea generally, so you can read more about this entire thing in this specific repo, but I kind of like to use it for small projects, right? I found an interesting application for LRU Cache and caching recursive calls to move from recaching to DP. If you want to have recursive factorial, you need to store only 2. Well, it is very interesting. So another interesting application I would think of it is, again, for instance, caching the web pages in a browser or in a HTTP proxy, or maybe you know, caching glyphs in a GPU texture, because as far as I know, on the GPUs, the size of the texture is limited, so you literally have a case of limited amount of memory, right? Is the size of the texture on the GPU usually limited? I think it is. GPU texture size limit. Right, because usually what you want to do, if you have several sort of like assets, you pack them into a single texture, right? You pack them in a single texture, but what if you have more assets that fit into single texture? Maybe you can start evicting the assets from the texture atlas and put in something more. So that could be, yeah, 64 kilobytes is the maximum size for a texture. Right, so this is actually a pretty good example, isn't it? Yeah, texture size limits in CUDA, and you want to do that on a single texture, right? Because it will make it easier to query a lot of things from a single like shader or whatnot, right? So you see what I'm talking about? So this could be another interesting example. You literally have a limited amount of memory on GPU. Or in case of the caches of web pages, you have a limited amount of memory on hard drive. So yeah, so but these are like memories on the different devices, right? So when we're talking about like caching stuff in recursive DP and stuff like that, we're talking about RAM memory, right? But the example in here are actually memory on the different devices, on different kinds of devices, which I find actually interesting. So maybe because the things that we're like solving on CPU with the RAM are usually like don't really matter that much. I don't know. Anyways, so let's actually continue and just implement a simple build system, right? So I need to take the header file, right? Let's just take the header file. It's taking some time for some reason. I think I did a click, and let's take the raw thing and just put it in here. So it's going to be no build.c, right? And I need to include, so as you can see, I'm editing right now not the main program, but the build program, the program that will build other program, right? So it's sort of meta program, right? If you think about it, the program that builds the program. I actually have to include the header file. Then I also need to define the implementation thingy, because it's a STB style header only library. And let's also include this entire thing, argc char argv, and let's do go rebuild yourself, right? So this is very important for the build system to actually rebuild itself when you modify the source code, so you don't have to do that manually, right? So so it needs to know your command line arguments that you provided, and so on and so forth. So the next thing we can do, we can call the compiler, right? with different flags. So we're going to enable all of the warnings. We're going to enable some extra warning. We're going to set the standard of C to 11, and we're going to be very pedantic about it, right? And we're also going to include the debug information in case we want to debug something. Then we're going to specify that the output of the compiler is going to be LRU, so this is the name of the executable, and the input is going to be the main C. I also like to, you know, collect all of that stuff and put it into a separate like macro, something like that. C flags, right? So, and then I'm gonna create this macro in here, C flags. There we go. So after that, we want to just, you know, return from it. So this is it basically, right? So, and we are doing the first thing, we're bootstrapping the build system, and yeah, of course I forgot to say something like no build. There we go. And after that, if I run this entire thing, it builds the main program, right? So we have a couple of warnings in here because we have unused you know, arguments and stuff like that. So let's actually quickly ignore them super quick. And there we go. So we have a build system that builds the main program and so on and so forth. We're not using any makefiles or any shell scripts or CMake. It's a very simple program, it doesn't really require too much. So we can build the whole thing with just a C compiler. What's up, good Duke? Hello, hello. How are you doing? All right. So the first thing we need to do in our program, we need to accept the input file path, right? So we're going to check how many arguments we provided. So if we provided more than one argument, actually less than two, that means the file path was not provided. We need to fail with some sort of an error explaining the user that, bruh, you failed with an error. It's going to be std error, and it's going to be error. Input file is not provided, right? Input file is not provided, and we're going to just exit with one. We might as well also print the usage of the program, right? So this is going to be the usage. We can put a program name in here, right? And say input txt. This is how you're supposed to use this entire thing. There we go. So now I can just run this entire thing. Unused argv. Oh yeah, and once we went past this entire condition, we're going to do char input file path argv 0, but it's still going to complain about unused argv 0, so let's actually quickly ignore it for now. Okay, so I actually want to see how it works. So we can try to run it, but another thing you can do, you can extend no build script and add support for subcommands for the build script. So if you have some arguments in here, right, you can check what those arguments are equal to, right? argv1 Zulu run. If the user provided run to the build script, we can go ahead and just simply like run the entire thing. Otherwise, we can say something like panic unknown subcommand, right? And we can provide the subcommand in here, like so. And let's just try to recompile the entire thing. So it's going to be no build run. No build run. There we go. So it says input file is not provided. So I can basically rebuild and instantly run the whole thing simultaneously, which is rather convenient, I think. So, and we can try to provide the Shakespeare.txt in here. There we go. There we go. Cool. So, and this thing does not complain anymore. So we need to read the entire file. So I already demonstrated this a couple of times. I'm going to simply memory map the whole file with a map call, right? So it's a POSIX call. It's probably not going to work on Windows, but maybe with WSL you would be able to compile it on Windows, right? And what it does, it can allow you to take a file and map the whole content of the file into the virtual memory. So it will make it appear, operating system will make it appear like the content of the file is just in the memory, right? And then you can just treat the entire content of the file as a string, right? So that's basically what it does. It can do a lot of other different things. It can allocate memory for you and so on and so forth. I actually, you know, explained how the syscall works in one of my videos on the main YouTube channel. So let's actually Google up something like Zoding mmap. Just Google up Zoding mmap. Yeah, why Linux has the syscall. So I'm gonna redirect you to this video if you're interested in how mmap actually works. Well, not, I mean, it doesn't explain how it actually works and how to use it rather. Right, my video about mmap syscall, right. If you want to know how mmap actually works, you probably want to watch Andreas Kling videos because he probably at some point implemented an mmap. I wonder if he can actually find any video where he actually sits down and implements mmap, because I would assume that he would implement that early on in his operating system, so I'm not sure if there's any documentation on how he implemented that. So Andreas Kling mmap, actually, let's actually see. Exploiting mmap. Well, I mean, yeah, private file backed memory with mmap. Oh, okay. So he implemented something. He implemented something about mmap, specifically the private map. Okay, so maybe you want to watch that. I haven't watched that video, so maybe I should actually watch it. It's like 1 hour. Okay, so I'm gonna actually put it in the chat and also in the description. So and I'm also gonna watch it myself at some point because I'm really curious actually. So yeah, if you're into like operating system development, maybe you're gonna be interested in this kind of stuff, but yeah. Can you recommend the best way to start learning assembly, maybe documentation or useful blogs? I don't know, to be fair. What I usually do is, I don't know, so here's 2 things to remember about assembly. Assembly is very non-portable, right? So assembly on different CPUs, is completely different language. Right, because assembly are just mnemonics of the CPU instructions, and on a different CPU with a different architecture, it's going to be a completely different thing, right? The instructions are going to be different. The semantics of the instructions is going to be different. The way you have to call them, the way you have to do all this stuff, it's all going to be different on a different architecture on CPU, like x86 versus x86 64 versus ARM versus MIPS versus Spark versus so on and so forth. All of these assemblies are going to be completely freaking different. Well, x86 and x86 64 are not completely different, but I mean, you get the point. So you have to keep that in mind. First thing you have is an architecture, right? So that's the first thing. It's so the first dimension. Second dimension is how your program written in assembly interacts with an operating system. If you do run on operating system, you may not necessarily run an operating system. In that case, you need to learn how to interact with BIOS or UEFI, but it's pretty much the same situation anyway. How you interact with an operating system. The interface between your program and Linux operating system is going to be different than interface between your program and Windows operating system, right? And also, if you don't have any operating system, like you're going to be interacting with like a layer lower, BIOS or UEFI, and so on and so forth. So you have 2 dimensions: the architecture of the CPU, what kind of CPU you're running, and what kind of operating system you're interacting with. And that gives you actually a combinatorial complexity. So if you're writing an assembly, for what processor you're writing it for, on which operating system. And believe me, this square of intersections of these 2 things is going to be a completely different experience. Are you writing assembly on x86 64 for Windows, or are you writing assembly on ARM for Linux? This is a completely different assembly, completely different world with completely different rules. And what exactly are you learning? Which word, which point on this square you're in? You have to first pick that. And once you pick, you have to Google. Right, so for instance, hello world in assembly x86 64 Windows. Right, so I picked a point on the square. Okay, so how do I write that? And now I can try to Google the tutorials and stuff like that. So I guess to start programming in assembly, first you need to understand that there is this, combinatorial complexity. So what is your, CPU and what is your operating system? And given that, you can start Googling and see how you do in that specific situation. You see what I'm talking about? Is that helpful? I don't know. I know nothing about assembly. I'm sorry. Okay, so we need to memory map the file. So let me see. So when we memory map the file, we need to call this scary function. This is a very scary function. But the thing is, it accepts two important fields in here. The length, how much memory you want to map, right? How much virtual memory you want to map. And what file is going to be that memory backed by. I think that's how we say it. So we need to obtain these two information. And you see, it doesn't accept the file as the file path, right? So the only thing we have about this file is the file path, right? So, but this accepts integer, and this is because it accepts the file handler, right? To get the file handler, we have to first open that file, right? So we have to call the open syscall. So it's going to be something like this. Here is the open syscall, and that thing already will give us the file descriptor. So, and of course, we'll have to provide the input file path and so on and so forth. Right, but how do we get the length of the file? Right, so we need to measure the size of the file before we can actually map it. Right, so here I can already say that we press an FD, but where do we get the length? So the length of the file is usually determined by fstat, right? So fstat syscall or something like this. Did it open it? I think something went wrong. fstat2 electric boogaloo. Right, and this one accepts, as you can see, it accepts file descriptor, which we already have, and a pointer to some sort of like a buffer, right, into which it will store all of the information about that specific file. Right, so there we go. And that specific structure is going to contain the size of the file in bytes. Size of the file in bytes, and so that means the content size is going to be equal to stat buff st size. There we go. So we have a content size in here, and we can use this content size like this. All right, so, but all of that is not finished, of course. We also need to provide the flags for the open function. Let's take a look. So I just copied a couple of functions here and basically interconnected them with each other just to, roughly outline what I need to do, right? Because memory mapping the file on Linux requires two syscalls. First, you have to open the file, then you have to query the size of the file, and then you memory map that file with that specific size. That's it, actually, right? So, but all of that requires like several parameters and whatnot, and you have to be a little bit careful. You also have to handle the error messages, errors from the operating system, for example, when the file is not available or something. So yeah, but apart from that, it's just like pretty straightforward. So let's take a look at the open syscall. So flags. As far as now, flags basically determine the mode in which you're opening this entire thing, and we're opening in read only because I don't plan to modify the file. I only need to read the file. Right, so I'm going to put it in here, and if an error has happened, this entire thing will just return you the negative file descriptor. All right, and in that case, you can say something like error could not open file as because of that. Right, so it's going to be input file path, and we're going to extract the error message from error no, and we're going to just exit with 1. There we go. Cool. So now we successfully opened the file, right, with the file descriptor. So fstat can also fail, right, and In that case, we also have to say something like could not get the size of the file as because of that reason, right? Because of this reason, and we're going to provide the input file path and also str error no, and then we're going to exit with non-zero exit code. There we go. We successfully got the size of the thing. So now I need to memory map everything. As far as I know, address is basically where you want to place the file in the memory. So we don't really care, so we're going to put a null in here. I think in case of a null, the operating system will just choose the address for us. West, the programmer, thank you so much for Twitch Prime subscription, really appreciate it. So protection thing is more about basically like read only, write only, or execution only, if I remember correctly, right? So let's find the protection. Yeah. So in our case, we're just reading the entire thing, so I'm gonna put protection read. So and flags determine the specific things, the specific behavior of that memory. I think in our case, we're gonna use private. Create a private copy on write mapping. Updates to the mapping are not visible to other processes. We don't care, we're only reading the file. And not carried through underlying file. I think this is actually perfect. And I think this is what Andreas Kling was implementing in his operating system, right? He was precisely implementing the feature that we're using right now, private file-baked memory. Yeah. So that's actually pretty cool, right? So I wonder if any other mmap related development are documented, but I'm definitely watching that session after today's stream. I think it's kind of interesting. So yeah, all right. So this is gonna be private, and yeah, let me see. So this one is gonna be something like this. And offset is basically offset within the file. We want to read the whole file, so offset is pretty much going to be 0, right? It doesn't matter. So, and here is basically the pointer to the content itself, right? So the content data, right? And of course, if content data turn out to be null, right? Usually, if the function returns a pointer and it returns the null, that means there was an error during an operation. This is how C works, as far as I know, right? So, and in that case, we can say something like error could not memory map file that because of whatever reasons operating system come up with. Input file path, str error no, right? So I really like str error because it just takes the error code, you know, from error no and generates a human readable error. So I can stick it up my log and it will work, hopefully. So as far as I know, all of this, yeah, so here is the first operation, opening the file, getting the size of the file, and then mapping all of that to the memory. And what it results to is just these two variables, content size and content data. So content data will contain the beginning of the string, and content size is going to contain the size of the string. And there you go, you have your whole file as the string with just 3 magic calls. 3 magic calls, and you have the whole file as a string. And as far as I know, the size of the file doesn't matter, so you can memory map like sizes, like files of any size. I think memory map like is not gonna load it into the memory until you actually try to access this entire thing, like by pages or something. I think it's like sort of lazily loading them in. I don't really know how exactly operating system works, but yeah, it's rather interesting. We're not loading big files anyway, so we're just loading some file. Yeah. Alrighty. So as far as I can remember, to use these calls, to use these functions, you have to also include a bunch of POSIX mumbo jumbo. Right, specifically this stuff, right? So here are POSIX things. It's only for open, right? Then for fstat, I think you have to include uni-std, right? Uni-std, and for mmap, you have to include mman for some reason. There's completely no system or like around the naming of these POSIX files. I have no idea why some of them are Cs and some of them are not Cs or something like that. It's just like, yeah, a complete mess. Complete mess. But it is what it is, and it isn't what it isn't. And of course, after you've done working with this entire thing, I think you should unmap the data, content data, and also close the file, right? There we go. Though, even though this entire thing is like a very much POSIX thing, I don't think it's gonna work on Windows, but on Windows you have their own calls for memory mapping files. Win API memory map files, right? I think it's done with the virtual alloc or something in the same way. I think virtual alloc just allocates the memory, but I'm not sure if it maps the file. What's the function? Okay, creating a file mapping object, okay. Creating the file mapping. I'm just curious. Create file mapping. Oh, there's literally a function called create file mapping. I'm not sure if this is the function that you're supposed to use. Just saying, because I'm not a Windows expert. I'm more of a like a POSIX. Well, I'm not even a POSIX expert, but I worked with POSIX more than I worked with WinAPI. Both of them are shit, by the way, but I work with POSIX more. So, and I don't know for sure if that's the thing you want to use, but it looks like the thing you may want to use, right? So you provide, it's really actually similar, right? It's actually really similar. You provide the file handler, you provide some protection attributes. We also have protection attributes, some other things, and it will probably return you some other handler. I'm not sure if it will return you like straight up a pointer to the memory, like a string, but maybe, I don't know. So yeah, so what I'm saying is that on Windows you will also have similar things, right? You also have similar things. Okay, after that we can try to maybe print the entire file, right? So we're gonna use fwrite for the entire thing. So we're gonna be printing the content content data, right? The content size is gonna be content size, and we're gonna print in one content, please. So this one is going to be std out, and there we go. And after that, I'm going to try to run the entire thing. And something went wrong. Yeah, we don't have str error. As far as I know, str error is available on string. And also you need error no if you want to use error no. Is that it? Oh, here you have to provide std error. So let me go through all of the printfs. Right, through all of the printfs and just see, yeah, I forgot to provide std error for all of the printfs. Classic. And when I unmap, I think when you're unmapping things, you also have to provide the size, right? So because it doesn't know how much you want to unmap. Okay, so, and we've got the garbage. Nice, I really like that. Cool. I've never actually encountered that before, but we basically mapped something and we tried to read it and we got the garbage. So that's cool. And this is because I was trying to read not the actual input file that we provided, but the executable file. So basically the program just printed itself, I think. I think the program just printed itself, but I don't see the header, the elf header or something. It actually didn't print like everything. That was really weird. Right, so I don't see elf in here, right? So I don't know exactly what happened, but that was funny. So the thing I need to do in here, I actually have to take the first one, not the zeroth one. All right, so and now we have the Shakespeare actually printed right in front of our eyes. Okay. So, and now we have the input, right? But now we need to actually split this entire thing by words, right? Because we're going to be treating each and individual word as an event, as this sort of query to how many times that word is encountered within the entire document. So what we're going to use is basically my library. It's called string view library. It's actually a very simple library. But I use it all the time when I need to parse something, right? I use it all the time when I need to parse something. You can find this library in here if you're interested in this thing, right? So, and this is the description, right? And string view library. There we go. So it's going to be available in here, and it's a header-only library. It's a simple header-only library that you can just stick into up your project, right? You just have to stick it up your project, and it will work. So it's actually downloaded in here. There we go. So the way you use it, you just copy this header into your project, then you simply include this header in here, and you define SV implementations because it's a STB style library, right? Implementation, there we go, and then there we go, it is available to you. The thing about this library is that it has a type called string view. String view consists of size, count, and a pointer to the beginning of the string. So you see, it's basically this pair of variables, but in a form of a structure, right? So the pointer to the beginning of the string and the size of the string. So this string view is basically like a very lightweight small window on a region of memory, right? And since it's so small and lightweight, it's literally two variables, right? You can easily manipulate it, and for instance, if you have big string, you can easily split it in half in O of 1 and have two strings, because the memory wasn't copied, you just changed the view on that specific region of memory, which allows you to quite efficiently parse things, right? So we have a huge file, you treat this file as a string view, and then you can chop lines off of that file and iterate line by line quite efficiently, and within that single line you can chop words, and now you're iterating word by word within a huge string without copying anything, without like allocating memory. So you just have a single buffer of characters, and you just view them with different sizes of windows and stuff like that. You see what I'm talking about? So that's basically what this library is all about, right? So we construct a string view out of two things, and then you can manipulate that string view with these operations, right? You can, for example, trim the leading and trailing white spaces. You can take characters up until a certain predicate is true. You can chop by a specific delimiter. You can chop an amount of characters. You can chop while. Right, you can find an index, you can compare the string views, you can check if it starts with a specific prefix, and so on and so forth, right? And all of that without allocating and copying chunks of data, right? All of that is on this small lightweight string views, which is just pair of these two, you know, just pair of these values, right? And all of that is actually very simple implementation. You can even implement it yourself. So for a long time, I didn't want to turn it into like a GitHub repo because I thought it's so simple, anyone can just implement it themselves. What's the point of having it as a library, right? So, and the size of this entire thing is just like 250 lines of code, right? But I was using this kind of approach so heavily that I needed a way to just quickly copy paste this thing and not implement it from scratch over and over again. So I turned it into a separate library. So, and yeah, you can find it on GitHub. So that's basically what it is. All right. So now you get the idea of how this library works, right? So, and the thing we can do, right, we can now, here we have a content data and content size. So I have a special function SV from parts. It takes the data and the size and gives you a string view. It basically builds the string view out of these parts, right? So that means I can do something like this. So this one is going to be content, right? And I provide the content data. Content data, then the content size, and there we go. I have a string view that points at the whole file. So I have the whole file in memory as a string view. And now we can, for instance, iterate line by line. While the amount of characters in the view is greater than 0, what we're going to be using, SV chop by delimiter. And if we want to chop by lines, the delimiter is obviously going to be a new line, right? And we have to provide the content by a pointer. So essentially what's going to happen, this thing will return a line from the content, and it's also going to modify the content so it doesn't have this line. So you have a string and you chop off like one thing out of it, you work with it, and that thing is modified. So that's why we actually pass it by a pointer, so because this thing is going to be modified. So, and then we can print everything line by line. So we're going to wrap it around with parentheses to indicate that we are iterating line by line. So NSV FMT, NSV args are special macros that expand to printf formats and printf arguments correspondingly to print string view. Since string view is a custom structure, right, it's not compatible with printf, right? So obviously you need to sort of adapt it to make it possible to work with printf. And in this specific case, SVFMT expands to this thing. So this format basically tells that you want to print a sized string with a specific size, and SVArg basically takes your string view and expands it into two arguments. So you think you're passing one argument in here, but in fact you're passing two of them because they get expanded accordingly. So that's basically what we're doing here. So this is how we use this entire thing. So that way you can print string views, because you cannot just print string views with $s. You can't just do that because they are not null-terminated, because %s requires null-terminated thing, right? So that's why you need to do this kind of stuff. Very complicated. Well, it is what it is. If C was a better language, maybe this kind of stuff would be implemented simpler, but unfortunately C is a pretty shitty language. And if you think there is a replacement for C, I have very bad news for you. Didn't printf allow custom format injection? Where? I'm not aware of it, I'm sorry. You think you heard about it, but you're so confident about it. Okay. All right, so let's actually see if this entire thing works. All right. And there we go. So as you can see, we actually parsed everything by line. So we can see the parentheses in here. And yeah, this is basically an indication that we parsed everything by lines without any memory allocation, without anything. We're just iterating through the views. All right, so let me see. All right, everything seems to be okay. Now, I probably want to ignore empty lines because there's no words in them, right? So if the line is greater than 0, right? If the line is greater than 0, only then I'm going to print it, right? Because as you can see right now, we have a lot of empty lines. Right. So now, did it actually do anything? Okay, so some of them contain spaces, right? Some of them contain spaces, and maybe because of that we want to actually trim the lines, but I'm not sure if it's necessary because we're gonna also trim the words themselves, right? So I don't think it matters that much, right? So the next thing we want to do, we want to actually iterate word by word, right? So while line is greater than 0, while line is greater than 0, what we're going to be doing here is word sv chop by delimiter this line, and we're going to chop by a space, right? So there we go. So, and here we also want to do something like if count is greater than 0, only then we're going to be printing this entire thing. So this is going to be word. And so interestingly enough, I think I also want to trim the entire thing. And now we are iterating everything by word. So now we are going through each and individual word in the document. Right, without any memory allocation, by the way. We're just like literally going through each individual word in the document, iterating with the string views. So now, if we're gonna count the words, I think counting the words case insensitively is not gonna be a good idea, right? because there's a lot of like case variation within the word itself, and also in some words you have special characters, right? We want to basically remove them, right? So for example, there's a knight that doesn't have a comma. Some of them contain like a close parent or something. We want to basically normalize our words and normalize our words and bring them to a specific case, removing all of the garbage and stuff like that. So basically clean up the data, right? We need to clean up the data that we have. So to do that, I think I'm going to introduce a new type. Since the words, right, are very small, we are going to basically store them in a very small structures, in a very small arrays, and that will allow us to actually how to say that, to actually pass them around by value, right? It will allow us to actually pass them around by value. So the way I like to do that, so let me actually see, we already did that. I think the maximum size of the word in this specific document is 18. If I remember correctly, is it 18? Because we already did that. But I want to actually do that one more time, just in case, right? So it's going to be size t, max word max len, and let's actually just you know, check it for one more time. And if word count is greater than word max len, we're gonna assign this entire thing to word count, right? Maybe we don't want to even print the entire thing because it will take too much time, because we are printing into Emacs, and Emacs is pretty slow terminal. So let's put it like this: max word len is going to be something like this, and so I have an inconsistent wording in here. Word max len, there we go. And there we go. So the maximum length is 18, right? Constantly allocating and like deallocating small chunks of 18 is actually kind of like lame. So I think, again, I'm gonna introduce a structure that just holds 18 characters for the words, right? Because we're implementing like a toy example anyway, so we're not trying to make a production ready system, and the problem itself is kind of like not that important. So we're gonna basically take a couple of shortcuts, and this entire thing will actually make a memory management way easier, because now string literally becomes a copyable value as integer. Right, so here's an interesting thing. You use integers all the time, right, in C. You pass them around all the time, but you never think about memory managing a single integer, right? Because you just put it there and just copy it inside of the function via the stack and whatnot. You just never think about it. But if you do all of the stuff with a string, right, for instance, if you return a string, right, something like this, you have to constantly think, is this string like, what does it point to? Does it point to managed memory? Who's managing that string? Right, you have to constantly think about it. But if you're returning an integer, like, you never think about who's managing that integer, because it's always passed by a value. There's nobody to manage it. Well, it's kind of managed, but managed by the stack, right? So in that case, it will move for, on the stack from one frame to another frame, right? So, and if you introduce a type like this, word that contains for instance 18 amount of characters, you turn a very small string into this kind of copyable data that you never have to worry about, right? So if you return a word, you don't have to think who's managing this string. You just return it by a value, just like integers. So the manageability of this type is as easy as managing an integer. You see what I'm talking about? Right, and the cost is basically, it's shorter, right? So, but you don't really need a long string in this specific example, right? So this is the constant trade-offs we're talking about, right? So, yeah. And on top of that, by doing that, you don't have a cost of even garbage collector, right? In a garbage collector languages, you don't think about that, but this is because you're paying with more memory and performance because the garbage collector does all of that things for you. But in this case, this doesn't even require any garbage collector. So this kind of things, like saying that I have a fixed size string, the only thing you pay with is the size of the string. But you don't pay with the runtime much, you don't pay with like other stuff as with garbage collector. You see what I'm talking about? It's actually very interesting. It's actually very interesting. So you basically say, okay, so this word is a small chunk of data that we copy as an integer or as a double or as anything else. So, and for this specific case, it just works fine, right? So it doesn't work generally, right? So, but for specific thing, for that small specific case, it works fine and it actually simplifies our lives. That's what's interesting. Right. Like I have an opinion that not every code has to be as generic as possible. In fact, when you write a code for very specific problem, very specific code that doesn't work generally for everything, you actually simplify your life, because then you have a perfect interface for your problem. It's just like perfectly fits, all of the small little details fit perfectly. But if you have a general, very generalized library, you always have a trouble of fitting this general thing into your case, and it's always difficult to work with. It's always not always does what you want and stuff like that. Like it's way simpler to just make things specifically for your case, and it just makes it easier. That's what I found, at least. I'm not a really good programmer, but that's what I discovered over the years of programming. Small string optimization in C++, I never heard of it. Did C++ people come up with a name for things that doesn't require a name? People like to come up with different names for things that don't really require a name. It's just like, yeah, I'm just putting this thing. Okay, so maybe it would be better to kind of align it, you know, so it doesn't, the compiler doesn't generate too much padding. So maybe we're gonna say that we're gonna have 32 characters in here, right? It's still pretty much the same shit, but yeah. Okay, so here's the word, right? And this particular type is going to be super useful to use, for example, in hash tables, right? Because in hash table, you can just treat it as a key, and you can very quickly calculate the hash of this entire thing without worrying too much about null termination or anything like that. Okay, so if we're going to have a word, right, we need a way to convert that, to create that word, for instance, from string view or from C string or something like that. Okay, so let's do something like this. Word, maybe SV as word. So this entire thing is going to accept the string view, right? And it's going to return the word, right? It is going to return the word. So we're going to create a new word on the stack. Then we're going to maybe zero initialize it. Since we're using C, I can straight up do something like this. Okay. And now I want to actually check something. I think we need to assert if you are trying to put something that is bigger than the word data, I think we should fail, right? It's trying to construct like a bigger word that we support. It's actually not count data, it's actually count. Right, after that I need to do mem copy. Oh, yeah, we assert less. Yeah, so we assert less. And we assert less and not equal, right? Because we need an extra character for null termination in case we want to use the data as a C string. Okay, so what we're copying in here, we're copying this thing like that. So this is the destination, and the source is the SV, right? So this is the source, and how much we're copying SV count, right? And then we can just return this entire thing. There we go. So this is how we can convert a string view into a word, right? So that's how we convert all of that. So we don't have an assert. We don't have an assert, and so word. It's not really word count. It's oh yeah, it's a data size of this thing. So we're taking the size of this specific array. right? Okay, so word max 18, but this is not what I wanted in here. So now, what I'm gonna be doing, I'm gonna remove this entire thing, right? And I wanna create a function now that takes a word, right? It takes a word and normalizes that word. So what it does, it removes special characters and also brings all of the characters to uppercase, for instance. So to bring it into uppercase, I think we'll have to include something like C type, right? So it's gonna be F. And yeah, so what are we doing here? So I need to create the final result, right? So this is the normalized thing, it's 0 initialized. And now I need to iterate through the input, right? So I need to iterate through the input and put things into the output, right? So what's going to be the easiest way to do that? We can do that with 2 pointers. We can maintain 2 pointers. The first one points at the data that we process within the input, and the one that points at the data within the output. Right, so we can have something like the pointer to the input, which is word data, right, and the pointer to the output, which is the result data, something like this. And while we still have something in the input, right, so this thing checks if we point at the multiminator, right, while we have something like this, we're gonna extract the character like this, and we're gonna instantly move to the next one, right? And if the character is alphanumeric, right, if it is alphanumeric, we're gonna be adding that thing into the output, right, like this, but we're also gonna bring it to uppercase and move the output to the next character. So, and after that, we can just return the result. So as you can see, we have 2 fixed buffers. For 2 fixed buffers, we create 2 pointers and we iterate from the input, and then we collect it to the output, right? So that's basically what we have in here. It's actually old classic C code. So not many people actually write in this style, but it actually works fine. So, all right, so we have this thing, and now we have a word, right? The thing we can do now, we can take a word and we can do SV as word, turn it into an actual word. So there's a problem. We have a type word. We have a type word, and we have a word as SV. So maybe I should call it word SV. Right. So word SV. That gives me that. All right. I convert SV to a word. Then I can try to normalize. Did I give it the proper name? I still call it like this. So it's going to be word norm. Right. Word norm, and we normalize the word, and then I'm gonna print this entire thing like this. So it's gonna be S like this, and there we go. And let me, oh yeah, of course I have to extract the data itself, right? I'm extracting the data itself, and I have to put this thing in here. And as you can see, all of the words are now normalized. Right, so they're brought to the uppercase and they don't contain any special characters. And we didn't have to do any single malloc or alloc or anything like that, because we just had like a small buffers of the words, and it works fine because we don't have a very big words anyway, and this is a throwaway code that is not going to be used in production anyway. So we're just simplifying ourselves life. Right, people quite often, especially young developers, right, they try to write as you know, generic code as possible, even for things that don't even require that. So how are you normalizing and only normalizing a read-only mapped buffer? Because I'm not. I can probably show you. So the whole process, right? Yeah, the word is stored in the stack, essentially. The word is stored in the stack. So here is your memory mapped file. So it's going to be mapped file. Within that file, we have words, right? We have words like this. So here are the words. Word. So we have basically a buffer on the stack. On stack. The size of that buffer is, I think, 32 bytes. 32 bytes, and this 32 bytes comes from here. Here's that thing. So as we go through each and individual word in the file, we are copying this thing into this buffer, right? And as we copy it, we bring all of the characters to the uppercase and removing any special characters like this. So this is basically the process that copies one chunk of memory to another one. So you iterate from the input and you copy everything. You copy only alphanumeric values and you always bring them to the uppercase. Right, as you finished, you take this small thing and output it to stdout without touching the main memory. So that's the whole process. That's the whole process that we have in here. It is a very simple process. There's nothing, there's no tricks, there's nothing special. Very, very simple. You don't need to modify the file. We're just printing it to the standard output. Does that make sense? So yeah, so the file, it's always read-only. We don't even mess with the file. We don't even mess with the file. All right, so yeah, we normalized everything. We just normalized everything. So the next thing I want to do, I want to be able to count how many times a particular word occurred within the document, right? So we're gonna create a function, something like size t word count, right? So it will accept string view, the content, it will accept the whole content. And then we're gonna accept the needle, right? The needle has to be already normalized, right? So that's quite important. And in here, we're gonna do the process, this entire process from scratch, right? So this is why this is the expensive operation. The expensive operation, right? As I already said at the beginning of the stream, right? So for LRU caches to make sense, you need a stream of events, an expensive operation that you may choose, and not really choose, but have to do on each individual event. So that's the expensive operation. The expensive operation forces you to go back to the beginning of the document and count everything up until the end of the document and return how many times the word was like occurred in there. So, and that's the expensive operation. Right, again, so this is a toy problem, right? So in reality, you wouldn't probably do it like that, but we do all of that just to demonstrate how technically LRU caches work. Like we need something that has a stream of events, an expensive operation that you have to perform on each event, but you may choose not to do that because you already cached some particular values. All right, so here we have to do the iteration one more time. So it's going to be content count greater than 0. Right, so we chop off the line yet again, SV chop by delimiter. So this is going to be content, new line, and while line is greater than 0, we're chopping off the words, SV chop by delimiter line space, and in here, essentially, well, we want to skip the lines that are empty, right? So we also want to trim so we can know the empty line, the empty words and whatnot. For SV count greater than 0. To be fair, maybe it doesn't really matter because this thing is never going to be empty anyway, right? So if I understand correctly, but maybe we're going to do that anyway. So then we have to do word SV as word. So here's the word SV. Then we normalize the word. I think it's a word norm. And after that, we need to see is this specific word, after all of the normalization, is equal to the normalized needle. And if it is, we increment the count. Right, but to increment the count, we have to at least define it somewhere. So we're going to define it somewhere here. Right, and then we return the count. There we go. Here is the expensive operation. So now, what we're going to do. So here is the word, we normalize it and whatnot. I'm going to actually save this in here. So this is going to be our needle. Right, and we want to count the frequency of that word. So this is going to be word count, and we need to construct the document completely from scratch because we want to force the counts starting from the document. Right, starting from the document. And then we're counting that specific needle. Right, there we go. So now, after we normalized everything and count everything, we want to print the original word. Here is the original word. Maybe I even want to call it something like word orig to indicate that it's an original word, because the normalized one, you know, is uppercase and stuff like that. So, and then we can try to print this entire thing like this. So svfmt, because the original one is string view. Right, and then here we print the frequency, and then we separate it with the space. Right, so then it's going to be arg word orig, and the frequency is going to be just the frequency. There we go. And after we finished the line of words, right, after we finished the line of words, we want to print the new line like this. There we go. So that should be it. And now, as you can see, we're going through the entire document, and well, that is very interesting. So something is completely wrong, right? I don't know what exactly. I returned the count, and so word count. So we start at the beginning. We're searching for this thing. We can try to actually go into the debugger. Let's actually go into the debugger. So I'm going to go here, and I'm going to create an additional subcommand for our build system. strcmp equals 0. Let's actually find it in the debugger. I think I want to do something like this. strcmp argv1 gdb equals 0, right? And the way we're going to do that, we're going to run GDB on LRU, right? So do we build with this thing? I think we do. And now I'm going to do no build GDB. So it rebuilds everything and it falls into the debugger, I suppose. Yeah, there we go. We end in the debugger. And what I want to do, I want to break on word count, right? And I'm going to run this entire thing. And let's take a look at, oh, it actually... Oh, you have to provide the file. So break on the word count. All right, then run with a Shakespeare, and then let's take a look. So what do we have in here? We have the content. If I print the content, it's the beginning. It's the, and this is the whole size of the document. 94,275 characters. And if we take a look at the size of the file, it's around that, right? So we basically treat the whole thing as the string view. All right. And we can also print the needle we're trying to find. We're trying to find the. All right, so everything seems to be okay. Right, we chop the line. If we take a look at the line is basically the entire thing, but the size of the line is 11, right? So then we're chopping off a single word. Right, a single word is actually 3 characters in here. So there we go. Here's the 3 characters, and it is equal to that. And now if I take the word, here's the normalized the, and now we're comparing everything, and we can already clearly see that, yeah, I forgot to put equals 0, right? So I really like step debugging because it forces me to actually go through each individual step, and I notice the things that I never noticed. But I mean, to be fair, if the C library, standard C library, was designed a little bit better, you would never have this kind of problems. To be fair, I find the strcmp very error prone. It is in fact very error prone. And here's the thing, how many times you need to compare a string lexicographically? How often do you compare strings lexicographically? I can rarely remember the last time I had to do that. Every time I compare the string, I just want a single operation. Is this mother flipper equal to the another one? So it is such a common thing that C could have just have a function that just checks whether one string is equal to another. You need a lexicographical comparison only when you sort in the strings. And like introducing this is basically the danger of this like generic interfaces. Like you rarely need to compare the strings lexicographically. And exactly, like when you actually do, you actually want something more complicated. So I think like, yeah, C just should have like a single thing that just answers, is this thing equal to another one? And that would actually eliminate so many errors in the C code. I mean, if you want to use C, I think we should have moved past C long time ago, but apparently we can't do that. Every time people trying to kill C, they come up with an overcomplicated language that doesn't solve anything and only remove things from programmers instead of actually empowering programmers, unfortunately. SV func for comparing string views, would that whether they are equal? But they are not string views in here. I don't know. I mean, we already found the bug, we already solved the problem, so there's nothing to discuss in here. And by the way, in string view, I have only SV equal. And since I actually started not equal strcmp, how does that contradict to anything I said, and how does it solve any problems that I actually outlined? Anyway, so the string view, since the beginning of this library, I never actually needed anything else but this. So I never actually needed to like compare string views lexicographically, because the only way I will need to do that if I want to put them in like a sorted array or in a tree, right? And I really didn't need that. Okay, so let me see. So that should solve the problem. Okay, so now this looks more like it. Sonnets, apparently it appears only once in the entire document. And so this is actually, Emacs is a very slow terminal, right? It's actually very slow everything. The thing we want to do, we want to probably redirect this entire thing and just see how much time it takes to process the whole document. Right, so how much time does it take to process the whole document? So if I remember correctly, it takes around like a minute or so. So how are you guys doing while we're waiting for this entire thing to finish? You're doing fine. Nice. Really glad to hear that. Debugging a cache. Same. So Emacs printing is only slow, not executing. Well, when you execute a program, you're executing an external program. Okay, so something is obviously wrong. Oh no, it's finished. Okay, so it took a minute. The program is not executing in Emacs, it's executing in operating system. Emacs is just display. Okay, so let me show you. Alright, so you have an operating system, right? So how can I do that? Like, yeah, I want a pretty OS. Here's an operating system, and here's like it encompasses like everything in here. Here's your operating system. Within the operating system, you have Emacs, right? Emacs is a program that runs within operating system. It runs within operating system, right? Then this program has an ability to run other programs, right? So in our case, I'm asking the program, please run an external build, right? An external build, right? So how Emacs does that? It asks the operating system, please execute the build, right? Please execute the build. The operating system then creates a new process that, you know, runs the build, right? This thing is running within operating system on the same level as Emacs, not within Emacs. The next thing that happens is Emacs also asks operating system, please establish a connection, right, through a file descriptor between my build and me, so I can read what this build prints to the standard output, right? And whatever program prints to the standard output goes into Emacs, and then Emacs displays it in this window. So when you redirect the output, you're eliminating the slow operation of rendering the output, and you're only running the build, because every time the program wants to print things, it sends it to Emacs and waits until Emacs is read it and printing it, and only then continues, because it needs to print everything sequentially. Right, so the question is, printing is slow, not executing. Executing is not slow because executing is within operating system. Emacs does not execute things. Emacs just asks an operating system and establishes a connection with a running process and just reads whatever the things is running. Does that answer your question? Some people call Emacs an operating system. Well, those people don't really know what is an operating system. All right. All right, so here is the, so it took around 1 minute, as you can see, right? It took 1 minute, and here is the output. I suppose it contains some garbage in here, but I'm gonna actually remove it. Info, cmd, yeah. So this is gonna be like our sort of like expected result. We're gonna use this file to test our cache implementations and see if it produces the correct result, right? So that's basically what we're gonna use in here. Let's actually, you know, put something like Shakespeare expected on this thing, and there we go. Okay, so what we can do to speed up this entire operation. What we can do to speed up this entire operation. We can discuss that after a small break, because I really want to make a small break. While I'm on the break, try to think about like what can you do to speed up this entire thing, and then we can discuss that and maybe implement that. We'll see, we'll see. The winner gets tea, that's for sure. All right, so of course, you have an expensive operation. And the first thing you want to do, you want to try to cache that expensive operation. So let's implement a common interface for our cache, right? So for instance, you need only 2 operations for the cache, like in our specific case. You want to try to query the cache, check if there's something in that cache, and you want to put something into the cache, right? So that's why we want to have something like cache get, right? Cache get operation and cache put. In our specific case, we don't really need more than this. So for some other situations, you may have like a slightly different interface for the cache. So this is not like set in stone or anything. So what we caching? We're caching this specific function, right? So it accepts word, right? And returns how many times the word was encountered in this specific document. So that means the key by which we're caching is the word and the value is the size. But again, this thing might be missing, right? So it might be missing in the cache. So we need to indicate that this specific key, this specific word, is not in the cache. So usually in C it's done by returning a boolean and returning the value via the pointer, like this. So so then later you can have some sort of a condition, right? If, right, you have a specific key, size t frac, right, then you use frac. Otherwise, not found. So this is a usual pattern in C, and so also not only in C, also in all the languages like Ada or Pascal, right? So you usually return a thing from an argument, right? And the function itself returns boolean indicating whether the operation succeeded or not, right? And that way you can just check and then use frac. And usual paradigm is that if the operation failed, the frac is never modified, right? So here, the usual convention, the frac must be equal to 69, right? If your operation fails, it shouldn't try to modify the output parameters, right? So not like a lot of languages don't really allow you to program in this kind of style anymore, but in C it is usually the thing. Okay. So, and we're gonna do a similar thing, right? So get is gonna be something like this. So for now, we're gonna have no cache at all. So no matter what you ask, we're always gonna say that we don't have that, right? And we're gonna ignore all the parameters. Right. So when you do cache put, we're just gonna do this thing. So it accepts key and value, and it's supposed to just put them in the cache, right? So this is going to be void, word, and frac. So, and this is where we're going to implement our cache, right? So we just put the implementation here, and the program should go faster, but we also need to use that cache here. So how are we going to be using the cache, right? First, we've got the needle, right? So this is where we looking at the word and thinking whether we want to do expensive operation or not. So we're going to do cache get needle, right? And I'm going to put the frequency in here, right? Frequency. And if we found this entire thing in a cache, we don't have to do anything. So we only have to do something if we didn't find it in a cache, right? If we didn't find it in a cache, we may want to actually perform this expensive operation like this, right? So we just perform the expensive operation. After we perform that expensive operation, we want to put the result into the cache. So this is basically what we have, right? So we take the needle, we check if it's in the cache. If it's in the cache, we'd never actually go into this branch and we just print it right away from the cache. Right, if it is in the cache, if it's not in the cache, we perform the expensive operation and put it into the cache. Since there is no implementations for these two functions, there's nothing gonna happen, right? So it's gonna be as slow as having no cache at all. So let's give it a try. Right, so it's probably not doing anything. So we can even take a look at the output. So we're outputting to out.txt. So here it is, and we can refresh the page, and we can see the file growing. Right, so that's how slowly it grows. Right, so, and it's gonna grow until it reaches the size of the original file, which is 164 or something like that, right? So it's gonna just keep growing. You see how slowly it grows. So we don't have any cache at all, right? So, and the reason why I introduced this kind of functions is because I want to actually have a special macro that allows me to enable or disable the cache at compile time, so I can compare the performance with and without the cache. Right, so we can introduce something like no cache, right? No cache. So, and if it's defined, no cache is defined, this is going to be the implementation of the cache, right? Otherwise, the implementation is going to be completely different, right? So I'm gonna put it like that. So, and by enabling or disabling this entire thing, I will basically switch on and off the cache, and the code down there, it just doesn't care. It always uses these two functions, and if you don't have a cache, they're basically dummy functions. They don't do anything, so you're not using cache at all. Right, so there's also style in C#. Oh yeah, in C# you have like a keywords like in and out. You can indicate the input parameters and output parameters. I do remember that, right? It's kind of like, huh, interesting. I never programmed in C# myself, so I don't really know much. Okay, so the operation has finished. So as you can see, we have no cache whatsoever. So how can we implement the cache? Right. So as we said at the beginning, LRU, right, stands for least recently used. That's what it stands for. Least recently used. Maybe I want to actually disable this entire thing. All right. So, and one idea that I have in mind is essentially to have an array, right? So again, like you have a pair of values and you need to store them somewhere. You can store them in an array, something like that. And maybe I want to actually have a thicker lines. So here are the values. You can store them in an array. Within a single array, you have a pair key, which is the word, and value, how many times it was encountered, right? And basically you have a sequence of this key value, key value, key value, and so on and so forth. So this is your cache. How can you implement cache get, right? How can you implement cache get? You can basically linearly in O of n look through the entire cache and check. Okay, so I'm looking for the key 1. Is it equal to this key? Okay, it's not. Is it equal to this key? Okay, it's not. Is it equal to this key? Okay, it's not. Is it equal to this one? Okay, it's 1, and I return the value and I use that value, which is actually rather slow. But you know what's interesting? It's faster than iterating through each and individual word in the entire document. Right. It is faster because you're iterating through less amount of things. Think about it. Right. So here we have like a linear array. So LA, linear array. And get is essentially going to be linear in that case. What's interesting is that, as already said, LRU makes sense when you have a limited amount of memory. If you have a limited amount of memory, there is no even need to think about eviction policies. There is no even need to keep track of who's used how frequently or recently or any of the stuff, because you just put everything into cache always. You don't have to evict anyone. So that means this entire thing has a limited capacity, right? So this entire thing has a limited capacity, and it has like capacity of n, right? So, and if you want to insert a new thing into the cache, you just append it at the end of the cache until you actually, until you actually ran out of memory. So in that case, put is going to be O of 1. So yeah, this is basically a linear cache, a linear fixed size cache without any LRU, right? We don't keep track of any recently used information. But now let's imagine that we ran out of this cache. What do? We need to remove somebody. Who can we remove? Well, as I already said, LRU is about removing the one who's been least recently used. So we need to keep track of that somehow. Well, that means that when we get something, we need to append, we need to add some additional information that this, for example, element was used recently. So the thing we want to do, we want to actually put it to the beginning in front of everyone. That will generally, not asymptotically, but generally speed up the lookup because you will find it faster. Right, and also Now, since all of the recently used elements are at the beginning, you can just always grab the last one because the last one is the least recently used. Right, but putting this entire thing to the beginning means that you have to shift all of these things. So your gets additional O of n. Right, so you have O of n linear time to just look up and find thing, and you have another O of n to just bring the thing to the beginning. Right, so you have n. Put, on the other hand, still stays O of 1, actually. It still stays O of 1, and you basically replace the last element. Right, so if you didn't completely fill your cache, you just append it. If you completely fill it, you always replace the last one. So this is a linear thing. But linear time is actually kind of lame, isn't it? It is actually kind of lame because we want to look up a little bit faster. How can we look up a little bit faster? Well, we can probably build on top of this frequency thing additional data structures that actually helps us to look up this entire stuff a bit faster. Would it make sense to keep bigger frequency items instead of least recently used? Well, in that case, it's going to be called differently. Is it LRU Cache instead of LRU? So yeah, it's going to be probably make more sense. You would probably be able to get rid of this thing or turn it into O of 1. But it's a different eviction policy, right? We're talking about specifically about the LRU eviction policy. So it's all about basically details, like what's the eviction policy in your case. Yeah. And because of there's so many different eviction policies and they're called differently, people starting to confuse all of the things together. So what is the cache? What is LRU cache? What is LFU cache? And it's all the same thing. It's all the same thing, and people just like, oh, what is that? Like, yeah. All right, so how can we speed it up? All right, we wanna do a lookup that is O of log n, right? O of log n, or better yet, O of 1, right? So usually lookup of log of n is some sort of like trees, right? Or sorted arrays, race, and so on and so forth. So you can try to do something like this. O of 1 is usually hash tables, right? In any case, you're gonna have some sort of a map, right? You're gonna have some sort of a map. So the second data structure is essentially gonna be some sort of a map. So this is the first data structure. This is the second one. Map, and that map is specifically designed to optimize this operation, this lookup operation. So it maps your key to, well, usually it maps it to a value and a position in this frequency array, right? A position in this frequency array. So usually it's going to be pair, right? So it's going to be a value that you want to look up. You can actually store the value here, right? Why not? Also the location of this thing within this array. So it points somewhere here. Something like that. It actually depends. You can actually move the value in whatever place you want. Right. So I'm just thinking, what would be the better way to visualize that? What would be the better way to visualize that? Because I want you to visualize the map also as an array, but it also makes it look like it's linear. That's why I'm struggling, because I'm not sure, how do I visualize that? Right. So this is going to be the second one. Right. So this is going to be something like this. Right. So my problem with this approach is that it makes it look like it's a linear thing, but in reality it's not necessarily a linear thing. But maybe in case of a hash map it is a linear thing, but in case of a trees and sorted arrays it not necessarily. But anyway, so you have these things that contain key and they refer back to these values, right? There we go. Maybe each one should actually refer to the unique one and so whatnot. Right. So the first array sort of stores the information about the frequency. It stores it within the position of the element, and the second one stores the lookup information to quickly find these things within the frequency information. Right. So for instance, if you need to look up in a hash table, you will in O of one find the element and grab this element from this array and just return it. Updating, like putting a new thing, will mean that you oh, and yeah, you also need to update the frequency. So update the frequency, you will have to bring this thing to the beginning and also update the pointer to the new one in this thing. So it's also going to be like around O of n. Right, and to optimize this operation, people usually use linked list, right? So you have hash and plus linked list to sort of easily and quickly bring an element to the beginning of the queue, right? So and the put into this entire thing is going to be basically O of 1 adding new element to the frequency and O of 1 adding the new element to the hash. Does it make sense? Not sure if it makes sense. Right. So, but the whole idea is you have data structures. The first data structure contains frequency information, right? How frequently something's used. But since the frequency information doesn't allow you to quickly look it up, you have a second data structure on top of frequency information that lets you quickly look up within the frequency information. That's the whole point. Right, so you solve the problem by introducing the cache, but looking up within the cache is slow, so you need to put additional structure on top of it to make the lookup faster. And that's why you usually have two data structures in here. Does it make sense? Not sure, like I'm trying to explain it, but that's basically how it works. Does anyone have any questions? For linear search, can we assume the list recently used resides in the second half of the array? Probably, probably can. Very nice and clean explanation. Yeah, so that's the whole idea. You can actually, if you don't really care about fast lookup, you can just put everything into a single array or into linked list and just deal with the slow lookup. But if you want to speed up the lookup, you put additional structure on top of it, you know, just to, you know, keep track of things and just make it a little bit faster. So that's basically what's going on in here. Let's try to implement this thing. Right, so the usual classical LRU implementation that I found on the internet, again, I know nothing about caches and LRUs and stuff like that, but the usual thing that I found is hash, like linked list for the frequency, for the queue, right? So because linked list makes it easier to bring the element to the beginning, indicating that it was recently used, and then grab the last element to evict it. So people usually used linked list for that because both of the operations become O of 1. And for the lookup information, people usually use the hash table and refer back to the linked list to find the nodes and do something with them, right? So this is like the classical combination of LRU cache. Linked list for the frequency information and hash table for the lookup information. I'm guessing one has to evaluate what's going on to happen more frequently, reads and writes. Yeah, it's all about like analysis and specific situations. And furthermore, LRU caches for this specific problem, as I already mentioned, they are not suitable for this problem. I just couldn't come up with a better problem because I'm stupid. Right. If I was a little bit smarter, maybe I could come up with a better problem to demonstrate LRU caches, but I'm just dumb, so that's the best thing I could come up with. So, all right, so we need a linked list. I'm not going to be implementing linked list on the stream because it's a huge pain in the ass and you need a double linked list. So we're going to use an implementation, a predefined, you know, predefined implementation, prepared implementation. So yesterday I actually quickly implemented a linked list. I implemented it in a very interesting manner. Right, so it's a tightly packed linked list, right? It's a tightly packed linked list. You can actually find this thing in here. This is a throwaway code. I don't plan to make it into a library or anything like that. I just like implemented it very, very quickly. So it's like a 200 lines of implementation. And of course, for people who's watching me on YouTube, let's actually put the description: tightly packed doubly linked list. Implementation. All right, so what does it mean? Tightly packed doubly linked list implementation. This sounds kind of weird, right? So usually, how do you implement linked list? Right, you allocate dynamically a node, right? You allocate dynamically a node. Let's not use squares, they're difficult to draw. Let's use like these things. You allocate dynamically a node, right? Then you allocate another one and you link them together like so. Right. Then you allocate more and you link them together like so, and so on and so forth. And here's the thing, here's the problem. You don't really know where exactly this thing will go into the memory. If you're allocating them sequentially, they're probably going to be stored sequentially within the memory. But if you're allocating them once in a while, your memory layout is going to look fucking crazy, mate. All right, so let me show you. Okay, so imagine that you allocated one node, and here's your heap, and this is where it was allocated. So here's the heap. You allocated a couple of nodes at once, so your nodes are basically allocated somewhere like that. Then you stopped allocating and growing the array, right? And you did some other work that allocated more memory in here. And then you need to push something into the array yet again, so your next node is located in here. Right, and they refer something like this. So here's next one, here's next one, and this is the next one, and so on and so forth. So, and as you allocate and deallocate things, you're probably going to be also deallocating these things. Your entire linked list is scattered across the entire heap. It's just like smeared across it, and the compiler usually, the program usually, the CPU rather, I think. The CPU has a hard time, you know, putting all of that into cache. You have shit ton of cache misses and stuff like that. So, and also it makes it super difficult to manage memory, right? Because you have to be super careful. You remove a new element, you have to, don't forget to deallocate it. And if you deallocate in your list, you have to actually iterate through each individual thing and deallocate it once incrementally. You cannot just deallocate your entire linked list. You cannot. You have to make as many deallocations as you made allocations. So linked lists are extremely annoying to work with, aren't they? If you think about it. And on top of that, they're not even solving any problems in modern computing, because again, they have so many cache misses and stuff like that. So they're extremely annoying data structure, and people still teach them in universities. I mean, for education purposes, I think it makes sense to teach them in university, but you also have to make a note that don't really use them in production, because there's so many problems with them. Come up with something better. So what did I do? What did I do? I made a very simple data structure. So instead of linked list, we have an array. Each individual element of that array is the node. Each individual thing is the node. Right, and all of the nodes are like basically connected with each other, like this or something like that. Right, so they're connected. And every time you add a new node, the whole array is reallocated, and all of the nodes are state packed, and the pointers to nodes to each other are done via the indices of this array. Right. Yeah. So the definition of your node, is going to be as following. You have to define a structure, and you have to define two fields in there, the previous and the next, and these are the indices within the array. Right, and the array is always state tightly packed, and it could be reallocated if it needs more memory. So, and since we're not going to be removing any elements from the list because we're going to be reusing the elements in the list, we don't have a delete operation or anything like that. So this is a linked list that is specifically designed for LRU caches. So I'm going to demonstrate how it works in a second. All right, so let me actually grab this entire thing, a row, and we're going to try to play with it, and I'm going to just show how it looks like. It's like a dynamic index. Well, sort of, yeah. All right, so, and it works in PRC, by the way. It works in PRC. So here's the linked list, and do you support batch appends? No, this is not a production. Okay, this is not a production-ready library. I made it specifically for today's demonstration because I didn't want to implement a linked list from scratch on the stream because it's kind of like going to be off-topic. Please don't use it for anything. It's specifically designed for LRU caches. It doesn't support all of the operations, only the ones that are needed for LRU caches. And furthermore, please don't use linked lists in 2021. For God's sake, stop using linked lists. I know that my tutorial doesn't really help with that, right? So because I'm showing how to use linked list. But I'm doing that for the demonstration purposes, right? So I think it is important to know what is a linked list and being able to implement one and stuff like that. But please, for the love of God, stop using them. At least, well, I mean, the situation is more complicated than you think, actually. You may have huge data structures on, for instance, secondary storage that look like linked lists. So yeah, saying that don't use linked list is not really helpful, right? So the situation is kind of complicated, you know? So it's really strange. Like, don't use linked list in a place where you could have just used a dynamic array, I guess. In any case, so let's actually try to demonstrate how this entire thing works. So we're gonna have LL. Does it have LL? Oh, I didn't even have implementation part. So you literally just include the entire thing into your project, and there you go, you have a linked list. So that's how we use this entire thing. And it doesn't even compile because ptr diff is located here. I don't remember where ptr diff is located, so it's probably located somewhere here. So std def, is that because I didn't include std lib? No, I did include it. That's really strange. So okay, std. Oh, I know why. Okay, I know why. So it's actually included here, and there we go. It seems to be working. So one thing I want to do actually, I want to create like a dummy entry point where I can experiment with things. So here's what we're gonna have. So this one gonna be hello. Yep. Okay, cool. So maybe I don't even want to output anything. Let's not output anything. Cool. Did it say hello? Yeah, it said hello. So how do you use this linked list library? It's actually very simple and very dumb. You define your node like this. ptr diff, previous, and next. And then you define what you want to store in that node. It doesn't matter what you store. You can store whatever the hell you want. The only thing that is important, it has to have these two fields somewhere. You can put them anywhere, actually. They have to have these two fields, and that's it. So how do you define an empty linked list? Well, you define it like this. So this is going to be something like access. And you actually set it to null. Here's your empty linked list. How do you push a thing into linked list? Well, you first have to push front a new node, right? You cannot push a value directly because the library doesn't know what exactly you store in there, right? It doesn't know what you store in there, so it only can push a new node with uninitialized memory, right? It pushes the new node. So after you pushed a front node, you can access this node by taking an index to the front node. This entire thing returns you an index to the front node, and you can refer to this thing and you can set it to 69. That's how you do that. Yep, seriously, that's how we do that. So you can also take a look at the back node, and it should contain also 69 actually. We can try to print it, right, so this is going to be D, right, and I'm going to try to take the back node in here, and let's try to print it. So it mallocs, it actually reallocs. It doesn't use malloc directly, but it uses realloc. Yeah, it uses realloc to update things and stuff like that. So if I try to, so this is B. Oh, it has to be, yeah, A. There we go, it prints 69. So you see, we put the 69 into the front, we updated the back, and it is 69. So let's actually try to do some other things. For instance, we can try to generate a bunch of like dummy numbers. For instance, Fibonacci numbers. Right, so let's remove that. So first two Fibonacci numbers are 0 and 1, and while A is less than 100, we're gonna be pushing a new node into the front of the list, and then taking the front, we're gonna be setting this to A. And then let's calculate the next Fibonacci numbers. So we need to calculate C, A plus B, then A is gonna be equal to B, and C is gonna be equal, and B is gonna be equal to C. There we go. So that's the next Fibonacci number. So that will push a bunch of Fibonacci numbers into the linked list. Right, so then how do you iterate this linked list? You can start iterating it from any end. It's a doubly linked list, right? So you want to define an iterator, right? So here's your iterator. It will be even easier to use for loop, ptrdiff. You start with front of the list, right? And you do that until the index becomes negative. Negative index is basically null, right? Because zeroth index is a valid node, so the negative one actually is null. So, and how do you calculate the next one? You assign I to access I next. That's how we do that. If I mentioned it already, but what is ptrdiff? It's a very good question. It's a standard C type. It's a standard C type. It is used for pointer arithmetic and array indexing, if negative values are possible. Program that uses other types such int may fail on 64-bit systems and so on and so forth. So basically it's a special type for storing information about differences between the pointers. Right, and here is the thing. So if you have an array that looks like this, right, and for example you take two pointers, for example pointer at the 5th element, and subtract a pointer from the 0th element, basically from the beginning of the array. What you will get, you will have an index in that array that points at, I think, 5th element. Yeah, it will point at the 5th element because of how pointer arithmetic works, right? So that's basically what it's needed for, right? So differences between the pointers are essentially indices within arrays. That's what they are. So, as already mentioned several times, there is not much semantical difference between pointers and indices in arrays. Pointer points at the memory address, at the absolute memory address. An index is an offset from the beginning of the array. It's also memory address. So to sort of like encode the semantic meaning, they created a special type, right, to encode the semantic meaning. Yeah, there we go. They even provide an example, so it's a pointer difference. So basically pointer difference is used to indicate that it's a pointer, but it's a relative pointer. Will it not overflow? It can be negative. This is a negative value. Program that use, yeah, pointer arithmetic indexed if negative values are possible. So it does not overflow, it becomes negative. It's allowed to be negative. And negative value usually is used as null, as in our case. Anyway, so you don't really have to think about it too much. Just treat this as an integer, which is an index within this array. That's it. So yeah, you don't even have to know what is pointer div if you're just using this library, right? Okay, this is how you iterate in this entire thing. And what we're gonna do in here, we're gonna be printing the values within the linked list. Right, so the value is A. So let's see what's gonna happen. And here are the Fibonacci numbers, but they are in a reversed order because we were pushing them at the front. Right, we were pushing them at the front. So the reason why we support only front operation is because when we are adding a new value into the cache, we want it to be recently used because it was just pushed into the cache, so we're pushing only the front. The library is completely open source. I do not recommend using this library for anything, but if you want to use it, you can extend it and add pushback operation. Right, so, and for instance, here we dump in this entire thing, right. And there is another very important operation, by the way. There is another very important operation. Move front. What this thing does, it accepts your linked list and an index of a node that you want to move to the front. And what it does, it just takes it, dismantles all the pointers and reassigns everything and moves it to the beginning, so it's going to be at the front. So that is again optimized for LRU caches, right? So you know the node, you can make it recently used by basically shoving it at the beginning. And since it's a linked list, it's going to be all of one operation because the only thing you have to do, you have to redirect the pointers. Right. So let's give it a try. So the back to back is 0 in here. Let's try the following operation. So after we printed everything, I'm going to try to do move front. And what I'm going to move at the front, I'm going to move the back at the front. Why do we need to be doubly linked, by the way? Because it makes it easier. Because when you take in the back element, right, you take in the back element and you need to bring it to the beginning, you need to know the previous element. So here is the thing, you at the back, you need to bring it to here. To bring it to the back, you need to know the pointer to the previous element to actually bring it like this, but you don't know it. So to know it, you have to linearly iterate, but we don't want to linearly iterate. You see what I'm talking about? You can store 2 pointers in here, but to store 2 pointers, when you remove this thing, you will need to know the previous pointers yet again to update the previous pointer. You see what I'm talking about? Like, you always, to take the back and bring it to the front, you always need to know the previous pointer. If you store the previous pointer, you need to know the previous of the previous pointer to update it. And to update that, you need to know the previous of the previous of the previous pointer to update that. It's easier to, like, it's not even possible probably. So you just need a double linked list, right? So you just need a double linked list, that's it. All right. So let's formulate the problem yet again, right? So we have that, then we are taking the back and we're bringing it to the front. I'm just demonstrating how to use this library. This is just a demonstration. So after we moved it, we're gonna print the thing. I'm gonna print the thing. And there you go. So the original was descending order. Then we said bring this thing to the beginning, and it did. Now this thing is at the beginning. There we go. So this thing allows us to push a new element at the front of the list, and then it allows us to take arbitrary node and bring that node to the beginning of the list. So that's the operations we want to have in a LRU cache, right? And all of that is implemented using linked lists and whatnot, right? So that's basically the library. So it's actually very easy to use. And after you're done, you have to deallocate all the memory. So you just do ll free access, and it will deallocate everything. There we go. So we can even basically do a val grind, right? So here's LRU, and then if I do val grind, as you can see, no memory leaks. So yeah, it deallocated all of the memory that it was allocating. So it also uses like a dynamic library, the dynamic array strat, where it pre-allocates a little bit more than it needs. So like a push is a little bit faster, right, and stuff like that. So yeah, the question is, where does it store its own capacity? If it constantly reallocates itself, where does it store its own capacity and how many elements is in there and stuff like that? So it actually requires like a meta information. Who knows how does it do that? The source code is there, you can actually look it up. Global variable? No, it doesn't use a global variable. You can, if you use a global variable, you won't be able to have several of them. You can actually have several of them. Set 62 nodes, yeah. So essentially, you point here at the beginning of the array, in front of, yes, exactly, store them in front of the nodes. You have the pointer to the beginning of the nodes, right? So, oh my god. Hey. So here are the nodes. Here are the nodes. And you have a pointer somewhere here. So that's the only thing you know. But the library secretly sneaks additional information right before the pointer so you don't see it. So this is a header, where it stores all of the information. It stores the capacity, the amount of elements that are taken, the front and the back. But you cannot see that because you only see this part. You can actually find it if you take the pointer and look back, but usually you don't have to know that. So, and that's why we have a separate free function, because you have to free not from here, you have to free it from here. So, and here's how it works. I can even show you. So here is the header. So this is the header that we put right before your nodes. So it contains count, capacity, front and back. And for instance, if you want to access these values, for example, LL count, so there's a function for LL count. We take your pointer, we cast your pointer to the pointer to the header, and we subtract 1, effectively taking this thing and stepping back by 1 header, finding the pointer to the header, right? So that's basically what we do. And then we extract the count from the header. That's it. So that's how easily we do that. So we take a pointer, we cast it to the pointer to the header, step back by 1 header, and there we go, we have a header. So, and we extract all the necessary information. This is actually a very old trick, believe it or not. I think Pascal did something like that. But yeah, and LL-free, right, LL-free basically does the same thing, and it just uses a regular free to free the whole thing. LL-free is a macro that redirects to free. So I wrap it in the macro just in case you want to customize free. Right, so yep, that's how it works. Alrighty, so that's basically the linked list that we're going to use. But linked list is not enough, actually, right? So as we said, we need 2 data structures. Linked list only stores information about the frequency, but just storing information about frequency doesn't help us to find the nodes very quickly, because we don't want to iterate this entire thing linearly. We need a hash table. So we're also gonna steal the hash table implementation from some other place. I didn't implement that hash table. I took it from the STB libraries. Do you guys know what is STB library? So it's actually a very famous set of libraries. So you have libraries for parsing and writing images, for working with fonts and stuff like that. And there is one small library in here, which is called DS. Right, so it's called DS, and it stands for data structures. And this library contains 2 data structure implementations. The first one is a dynamic array, and the second one is a hash table. Right, so it has a hash table implementation, and we're going to use it as well. Believe it or not, I my linked list implementation was inspired by STBDC implementation, right? STBDC implementations implemented in a very similar way. I'm gonna show you how. Okay, so let's actually grab the this thing. I'm gonna actually put that thing in the description as well. So where is my description? stbds.h, and in the header itself there is a gentle introduction into this library, right? So you can find it in here. So I'm gonna put it in description because you can just follow the header. So it is in the header and it just explains how you're supposed to use it. But a spoiler alert, you use it similar way as you use linked list, because I based my linked list implementation on STBDC. It's actually very, very cool. Okay, so did I download this thing? I think I didn't. We need to grab the raw thing. Yep. And this is, by the way, something that you probably do want to use for the situations when you need a hash table. Unlike linked list, please don't use this linked list for anything. This is just for demonstration purposes and stuff like that. Okay, so let me see. So the way you use this library is just include it. Just include stbds.h, and you have to also define stbds implementation. Right, so let's try to compile the entire thing. No, this is not how we compile it. You have to do no build. Let's just run no build. Okay, so, and everything compiles, as you can see. Everything's fine. Everything's fine. Okay, so let's remove this entire stuff. First thing you need to do, you need to define a single cell in single cell for your hash table. And a cell is essentially going to be a key that you want to use and the value. Right, but value is not really necessary, right? Because the hash table allows you to query these cells by a key, so you can put whatever value you want. So maybe in this case, I'm going to just call it frequency. So, and you define an empty hash table the same way you define an empty linked list, like this. Seriously. And it even uses the same header trick. Seriously, it uses the same header trick. So I completely stole this implementation from STBDS. So, and you want to put something in there, right? Right. So we're gonna use put s, which actually, yeah, if you actually put something like value, right, we'll be able to just put this thing like this. Right, so this is gonna be t. The key is gonna be, so the key is word, so I need to construct this from string. Sister as word, so we're gonna put hello, and the value is gonna be 69. So I don't think we have sister as word, so I'll probably have to implement it. Oh yeah, I do remember this one, so this is something that you'll have to fix. Yeah, we don't have a sister as word. Okay, so let's implement it real quick. So we need a function that accepts cstring. Right, it accepts cstrings and returns you a word. Sister word. There we go. So we're gonna allocate the word on the stack. We're gonna, oh boy, also probably take the length of the word. So we'll have to do something like len str len sister. Then we're gonna assert that the length is less than size, the capacity of the word itself. Right, and then we're gonna memory copy this entire thing into here. So this is gonna be len, and then we're gonna return the word. There we go. So now we can do this thing like that. There we go. So it seems to be working. Okay, so let's actually push a couple of more words in here. So something like world, and this one is gonna be 420. Right, so we push all of that into the hash table, and now we should be able to query these things. So for hello, we're gonna have this value, hm get, I think, hm get, yeah. So we can query this thing directly. So it's gonna be t, and we're getting hello, and then world. So as you can see, we can put things into the hash table and we can query them back, right? So, and so this is a long, oh, this is a size T, so that means this thing has to be something like ZU. There we go. And probably want to run it. There we go. So hello is 69 and world is 420, right? So you see, we managed to put something in the hash table and we managed to query something from the hash table, and it's free in this entire thing is also HM free, like this. So the reason why I implemented a linked list in a similar style is because we have two data structures and you work with them pretty much with the same style, so it makes the code while you implement things more or less consistent, right? So, and after that you can check with the val grind, and I think val grind is going to be happy, right? So there will be no memory leaks, right? So it allocated things dynamically, right? And then it cleaned everything up. So this is basically two libraries that we're going to use, right? Very simple ones. Do you know what's the hashing function they use? Yes, it's like in the library itself. Hash function. So they even something like this one by default is to be hashes using a weaker variant of SIP hash and a custom hash for 4 8-byte keys. On 64-bit platforms, you can define the above flags to force STBDs to use specification compliant SIP hash to 4 for all keys. Doing so makes hash insertion about 20% slower, but on 4 8-byte keys 5% slow on 64 bits, and so on and so forth. So it uses SIP hash, and I wonder if you can customize that thing. Well, I mean, you can customize this thing. This library is 2,000 lines of code, and this is the entire library. You can just go ahead and put your hash function right in the library itself. So you can customize that, right? As I always say, the most reusable code is the one that you can copy paste and modify, not the one with the generic interface and shit ton of implementations and stuff like that. So this is a very reusable code. You can have a different hash functions. You can just go ahead and modify it. So we can even try to find SIP hash, right? Type dev SIP hash. STB hash bytes. Okay, so here are the functions. You can probably replace something from the std hash bytes. Oh yeah, there we go. So here is the hash function. So if you use stb SIP hash, it's going to use that. This is the custom one. You can basically remove this entire thing and just put your hash implementation in there. So here it is, if you want to. So this is the hash function that they use. Cryptic code. I mean, it's a, well, yeah. It's a cryptography, is it not? To be fair, hash tables for hashes for the hash tables is not really cryptographic ones, but maybe they are, because you don't want to like expose your hash table for attacks and stuff like that. And there's even like a statistics on measuring on particular machine. So yeah. So the fact that they so easily found the place where they calculate the hash function actually says a lot about these libraries. These libraries are really cool because at any point I can just like find the place where the library does the thing and just modify the thing. I don't like this hash function, I can replace it with something else. Sure. Are you using signals to implement the LRU? I'm using slots instead. I think slots are a little bit better. All right, so let's see. So I demonstrated both of the data structures that we're going to be using, right? And let's go ahead and implement an LRU cache. So the LRU cache is going to consist of, okay, so we have two things: no cache and the cache. So to be fair, for no cache, it would be way easier to just define a couple of macros, right? So let's define cache get, and it accepts these two things, and we always return false, right? So basically, you never have a thing inside of the cache. And in case of a cache put, right? In case of a cache put, we just do nothing, right? So it's an empty statement. There we go. So this is basically no cache. If you do have cache, we have something like, we have two things, right? We have two things. We have a table, right? And the queue. Queue. So the queue only stores the key. It only stores the key in the table. So because we use the queue as the frequency information, and the frequency is stored in the positions of the nodes, right? It stores in the position of the nodes. The closer it is to the beginning, the more frequently it is used, and we always evict in the last one because it's the least frequently used. So yeah, and of course, since it's a linked list, I have to put ptr diff t, so it's going to be the previous one, and this is going to be the next one. So there we go. Here's the queue where we store the sequence of keys, right? So, and the table is going to be what? It's going to use the word as the key, and for the values, it's going to store the frequency, the actual frequency, and the pointer to the node in the queue. Right, so we need to be able to actually find it back in the queue. So how are we going to be storing all that? So we know that we refer to the nodes via ptr diff, and we're going to call this thing queue index, right? Because the pointers are the indices. So through this entire thing, the cell in the node points back to the thing in the queue, right? As we showed in the diagram here, right? So here we have a frequency information, and here we have a lookup information. And the table with the lookup, it points back to the queue. So yeah, this is the frequency information, and this is the lookup information, two things, right? So, okay, when you need to get a word from the cache, how are we going to be doing that? So we know that the frequency that we're looking for is stored within the table, so we need to look up the table. hm get, I think, s, and that will, I think that will give us, I think you need to do hm get I, because it will return an index. All right, so we provide the table, and the key we're using this thing. So might as well actually maybe call it the key, and I'm gonna call the word. So this is the index. It's an index within the table. So you see, it also uses indices to refer to specific cells in there. But if the index is less than 0, that means we couldn't find anything, right? And maybe we're gonna always work when we can find something, right? So, and if we can find something, and the user provided the pointer to the frequency, we're gonna set that frequency like so. Table index frequency. So as you can see, we returned the frequency to the user, right? Now, what we need to do, we need to update the node that the thing points to, right? So essentially, we hit the cache in here, right? We hit the cache in here, we return the value from here, and now we need to take this node and bring it to the beginning in here, right? Because it was recently used, right? Because we indicate how recently elements used by basically moving them to the right. To the right we put the recently used, and because of that the least recently used go into the right. In isFrag is the context, okay, so probably, I think you're right. Let's actually call it value. You're right, so let's just call it value, right? Because that's what it is. Yeah. So we're getting a value from a cache, and maybe because of that, this thing is going to be just a key. So here's a key, here's a value, and you look up the key. You look up the key, and if the key is available, we return that value from the table, right? And then what we need to do, we need to take table index q idx, and we need to move the node it refers to the front. That's it. So you see, here we hit the cache, then we return the value from the cache, then within this cache we also have a reference to the queue, and we bring that specific node to the front, indicating that it was recently used. That's it. So, and on top of that we have to return true, indicating that we hit the cache. You can use this value if you want to. There we go. If we didn't hit the cache, we just return false. You see how simple it is, right? Hash table, queue. Hash table refers to the elements in the queue. We hit it, we return the value. If we hit it, return the value, we bring that element to the front, indicating that it was recently used, and it's quite unlikely that it's going to be evicted. Right. So pretty straightforward. Let's try to recompile the entire thing and see if it is working. So it's going to be no build. Everything seems to be compiled. Cool. Now we need to put something into the cache, right? Now we need to put something into the cache. And I'm thinking that there's two situations: when the cache is full and when the cache is not full. So we need to actually bring some sort of information. What's the size of the cache? What's the size of the cache? So let's define cache capacity. Cache capacity, and how many elements do we want to actually put into the cache? Let's say 256, right? Again, LRU caches are not about going super fast. It's about going as fast as you can, given the limited amount of memory. But if the memory is unlimited and you've been like clever about things, you probably can go even faster. Right? LRU is not about being as fast as possible. It's about being as fast as you can, given the memory limitations. Right? So this is the part that a lot of people forget when they talk about LRU. So this is quite important in my opinion. All right, so when we put things into the cache, so is the cache full? We can at any point query the amount of elements in the queue. So this one is actually value. So this one is the key. So we're taking a look at how many elements we have in the queue, and if it's less than the cache cap, is that also stored in the header? Yes. We store everything in the header, and you can basically query all of that information from the header. You cannot query capacity, but I never actually needed it. So the only things that are needed are count, front, and back. Yep. So it's very fast. You don't iterate through this thing. All right. So if we still within the cache capacity, what we're gonna do, we're just gonna push at the front a new node. Then we take the node at the front. We know that we pushed it at the front. We take it at the front and we set. So what's the queue? So it has a key, so that means we need to put a key like this. Okay, so we added a new thing at the front. All right, so we added the node here. Nice. Now we need to add a new record to the hash table. Right, so I think this ds had a chmput s, which actually allows you to put the whole record in there. Right. So we can put it like that. So this is going to be the table, and let's construct the table that we want to actually put in there. So this is going to be the item, right? And so what do we have in there? Key, value, and queue index. Okay, so the key is the key, right? The value is the value, and the queue IDX is the front in the queue. Right, there we go. And then we pushing that item into the hash table. There we go. But that only makes sense if you didn't hit the cache capacity. You just keep piling things on top, and that's it. So you add a record to the queue and then to the hash table, also referring back to the front of the queue. So pretty straightforward. So what if you hit the cache capacity? The type is item. Maybe it is. So the reason why I call it like that is because you sort of define a table, Okay, let's rename it to item. I think you're right. Let's actually rename it to item. Thank you for telling me what are the things are confusing. So yeah, maybe I'm gonna even call it like that. So table is a pointer to an item, and queue. Well, it's queue. It should be also confusing, but I don't know. We can call it node probably. Yep. So we have a node and item, and pointer to the node is a queue, and pointer to the item is a table. Okay, that's a little bit better. Thank you so much. I really appreciate the feedback, by the way, because like sometimes for me it's unclear what could be confusing, right? Because I'm the one who wrote all of that, so I have the full context in my head. But for people without full context, it could be really confusing. So thank you so much. Really appreciate it. So yeah, now it's a little bit like makes more sense, right? You have an item. You put all that, and let's actually go to the compilation errors just to... Oh, okay, actually refactored it first try. Oh, I know why I refactored it first try, because this code is disabled. Because we defined no cache. This code is only visible when you disable no cache, when you do have a cache. That's why everything compiles perfectly first try. So yeah, let's... Are you sure? Okay, I actually first tried it. Okay, nice. So... Cool. So let's continue. Okay, so we looked at the situation when we still have a little bit of a cache capacity, right? A little bit of a cache capacity. What if we don't have a cache capacity anymore? Well, we have to evict the element from the cache. And as we mentioned, the element that we're going to be evicting is the back one. There we go. So we're going to be evicting that element from there. So, okay, so let's actually try to see what do we have in there. We have a linked list, right? So it's a doubly linked list, so I'm not going to put any errors in here, so this is a double connection in here. And this thing refers to the empty one. So, and this is the one that we want to evict. We want to evict the one that is the last one. But there is somewhere in a hash table a cell, an item that refers back to this thing. So what we have to do, we have a key. We can find this element by the key, right? And we'll have to remove it from the hash table, right? So let's go ahead and do that. So we have the key. We need to find this element in the hash table. So that means I'm gonna do q like this, and here's the key. And how we're going to be actually getting it. So I remember there was a function get. I think like we always know that this thing exists, so we can just go ahead and just delete it right away. Yeah, so we can just go ahead and delete it. Yep. del table q. There we go. So essentially we finding this element by this key, and we straight up deleting it. That's it. It doesn't exist anymore. It's removed from the hash table. So after that, we probably don't want to allocate a new node. The only thing we want to do, we want to bring this node to the beginning and fill it with the new values. Right, that's what we want to do. We want to fill it with the new values. So the next thing we're going to be doing, we're going to do ll move front. And we're just moving this entire thing to the front. So it would be also nice to maybe... is that the key? Yeah, here's the key, and that means... Yeah, this is what I have to do. So, yeah. So I'm taking the back of the queue, and I'm moving it to the front of the queue. Right, now this entire thing is at the front. It is at the front. So after that, I have to form a new item. I'm forming a new item, which is also going to have like a new key, a new value, and it's going to use front like this. And we're going to be pushing it back into the hash, right? So yeah, so we moved this entire thing to the front, attached it here, right? And then created a new record and pointed it back to the new one. So that's how we evicted an element from the cache and created a new one, maintaining the same amount of elements within the cache. Right, so, and what's interesting is that we ended up with a situation when these two parts of the branch are the same. So I might as well actually just move this thing in here. and I think it's gonna make it a little bit more readable. Right. So if you have a little bit of space in the cache, you just push a new node and you just connect that node in here. So if you don't have any space, you remove the last node and you move the back to the front. But I think I forgot another thing. So after you moved it, you have to update its key. But since now we have these two things repeating in here, I might as well actually move them in here. There we go. So yeah, there we go. You have a space, you just push a new element at the front, you set the key, you set the item, you push to the hash table. If you don't have any space, you delete the last element, you move the last element to the front of the queue, and there you go. We have a new thing in here. All right, so this is basically the whole classical LRU Cache implementation with linked list and a hash table. This makes sense. So there is a lot of details in here, but the main thing, the main idea, as I already mentioned, you have two structures. The first structure stores the frequency information. The second structure stores information to look up this thing quickly. I'm gonna miss the point why I have to update the key in the queue. Because we are replacing it with a new one. Okay, we need to put a new value into the cache. The cache is full, right? So this is the key we want, but at the back, we have the key back. So what we want to do, we want to remove this element. I'm just bringing this element to the beginning, and I'm replacing this element with the key I want, effectively forgetting about it. So that's why I'm setting it, right? Because I'm removing that element, I'm removing this key. So that's why I'm resetting it to something new. So it's going to be like evicted from the cache completely from now on. That's why I'm setting it. But maybe I should take a look at the one. Yeah. So that's basically what's going on here. Does it make sense? Because I'm removing it. So I'm replacing it with the new key. Because this one is not needed anymore. So it's the one that we are evicting. Okay, so let's see if it's gonna work or not. So is it compiling? Oh yeah, I do remember there's a little bit of weird stuff in DS. So I think I'm gonna put the clank. No. In expansion of the... Yeah, so it's only just a warning. Okay. So if you compile it with GCC, it produces this really weird warning because of specific features of GCC. So one way to get rid of it is actually to compile with Clang. So to be able to compile with Clang, I want to actually do the following thing. Usually build systems support the environment variable called CC, where you can customize the compiler that you use for your build. So we can try to do the same for our build. So I'm going to create a function CC, which returns you a string, right? And so this is going to be the result. I'm going to get whatever we have in the environment variable, right? And if this thing is available, we're going to be returning that. Otherwise, we're going to be using CC by default, right? And I'm gonna put CC here like this, so that way I can customize the compiler if I want to, right? So it's not a rest, and also that means I'll have to do something like this. There we go. So now I compile with Clang, and there should be no warnings in here. Yeah, so there's something weird with my specific GCC in here. Okay, so we implemented the cache. So the whole cache implementation is like having already predefined data structures is 46 lines of code, excluding linked list and hash tables. So this is basically the whole logic. The logic of the cache is like this. Yeah, so if you want to learn more about it, I'm going to put this in a GitHub so you can ponder on this implementation, just to understand what's the logic behind it. So let's try to put it in practice, right, and see if it's gonna crash our our entire program or not. Also, it would be nice to clean up everything after the cache, because we need to clean the memory allocated by the queue and by the table. So maybe we're going to introduce another function, something like void cache cache clean up, right? Something like this. And here we're going to free the queue, and also we're going to free the table. Don't forget to change the main. Okay, thank you. I mean, yeah. All right. So, and for no cache, we're gonna have cache clean up. It's not gonna accept anything, but it's gonna be just empty thing in here. Okay. So, and after everything in here, I'm gonna do cache clean up. There we go. All right, looks cool. So the thing I want to do, maybe we want to actually like put some code that measures the memory within the build system itself, right? We can actually call this entire thing with time, right, to print the time. That will print us the time. Also, it would be nice if the build system itself automatically redirected it to a separate file so it doesn't spam Emacs. So no build supports redirecting like so. So you do the chain and you redirect it to the separate file like this. Right, and after that we can probably call another program that just checks that the output of this entire thing is the same as the expected output, and we have expected output in this specific file, right? So we're gonna put it like that. So you see, using no build is just like doing shell button C, right? But you have a C compiler everywhere if you have like a standard compliant C compiler. Right, and shell scripting languages are different depending on the platform. It's a mess. Trust me, it's a huge mess. All right, so, and let's just try to run this entire thing and see. So maybe we can disable the cache and let's take a look at how the performance looks like without the cache. So I'm gonna say no cache, and let's just do the run. And I think it's gonna be like around a minute or something. So you can see the build system also redirects to the file automatically. And yeah, so it's gonna take around a minute, right? So does anyone have any questions while we're waiting for this entire thing? I'm gonna put all of the code into the GitHub. So the entire logic of the cache is actually really simple. So you can just like look at it and ponder as you would at mathematical expression, and just follow the logic and understand why the things go like this. You can even try to draw how the nodes move around and stuff like that. And the entire logic is relatively simple, seriously. You can find the documentation of what all of these functions do in the corresponding files. Right, so LL move front, right? So here is the description of what it does. In the hash table, hm get. Right, so here is the documentation of what this function does. So the hash table is for storing a word and its corresponding value, and the linked list is for frequently usage. Yes, 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 100% correct. Right, so you can basically only use a queue if you don't care of fast lookup. The hash table in here is only to make finding the thing in a cache faster. If you don't want to find it faster in a cache, maybe you don't even need hash table. As a matter of fact, we can try to do that without the hash table and see how the performances differ. Okay, so this took like around a minute, right? So this is without any cache. Now, I'm gonna enable the cache, and I'm gonna set the cache to 256. So without the cache, minute, slightly more than a minute, with the cache. So let me see if it's going, if it's, oh, it's writing something, so I wonder if it's gonna be faster. It could be, it might necessarily be faster. Measure memory too. I don't really know how to measure memory. Measuring memory is actually a pretty difficult task, because how do you measure it? So are you measuring virtual memory or something like, it's also allocates and deallocates the memory. So it's kind of hard. Okay, by allocating a cache of just 256 elements, we managed to cut down the entire time in half. So yeah, and we also compared it with the expected output, so it produced the expected output. So this is not the fastest possible solution, by the way. This is not the fastest possibles, but it's fast enough given this limitation of memory. We don't know precisely how much memory we use because it's kind of difficult to measure, but you can control the amount of elements and see how much fits in there. We can go and allocate more elements, and the more elements you have, the faster it will go, but there's also like a point of diminishing return where no matter how much you allocate, it's not going to go faster anyway. So let's actually allocate like thousands of these elements. So how much memory will it take? So we'll see. I hope it's actually recompiled thing. And as it go any further, it should actually speed up. Did I save? I don't really know. Well, it didn't go that much faster. As far as I know, the fastest it may go if you like give it 3 kilobytes, but that's about how much words you have in general in the whole document. So I don't think it's gonna go any faster. So at some point the performance is constant. Yeah, pretty much. I can cut it down. I think you can cut it down up like to 10 seconds. When I'm not streaming, I think it goes to 7 seconds, but I'm also streaming, so, and I'm also recording to the hard drive, so hard drive right now is a little bit busy. So that may also slow it down a little bit. All right. So, and here's the LRU Cache. This is literally the LRU Cache implementation, like the one that I found in the internet, right? So like I looked through the internet just to see what people implement, and apparently it's just a combination of the queue, linked list queue, and a hash table, right? So in a queue, you store the frequency information, and in a hash table, you store the lookup information to make like finding this entire thing a little bit faster. And that's pretty much it. That's pretty much it. And as I already said, I think you don't really need a hash table if you don't care about fast lookups, right? And we can try to implement something like that as well. So let's actually implement a cache that doesn't use hash table and only uses the queue to store frequency information and just like search this thing linearly. We can try to implement it as well. So maybe before we do that, I might as well actually do a committee and then push it. So I actually removed the experimental repo that we had at the beginning. So we started completely for a fresh one. All right, so let me create a new thing in here. Git init. Right, so I'm going to initialize this entire thing, and let me see what kind of garbage I want to exclude. So I want to commit that. Do we need anything else? I don't think so. So I'm gonna git ignore LRU, no build, old, and out txt. Right. So let me see now. There we go. Ready, set, go. And maybe I'm gonna write a simple readme in here. LRU implementation exercise. Is that how we spell exercise? I don't remember how I have I spell. Nope. I forgot how to ignore. Yeah. Okay, so this one I have to LRU. So quick start. This project uses no build, https github.com no build system. So this one is going to be console cco no build.c no build run. Right, and the license is going to be MIT. Add readme and license. So let's create this repo. I also added Shakespeare. So it's committed in the repo. So and also expected output as well. So LRU LRU Implementation exercise. So this one's going to be public and create repo. So I think this is going to be a solid 4-hour stream for sure. At least not 6, which is nice, right? Which is watchable at least. Okay, so I'm gonna push that right to the repo. Right, so here is the thing. There we go. You can find the source code in here. So, and also for people who's watching on YouTube, I'm going to put it in the description. Source code. There we go. This is going to be here. All right. Now, yeah, what I want you to do, I want you to, let's actually try to implement the idea where we don't have a hash table, right? Why do we even need a hash table? Right, so to make the things like lookup faster. But if you don't really care about fast lookup, you don't really need that. And even if you don't have a fast lookup, your lookup is going to be relatively fast because the recently used things, frequently used things are going to be near the end. So they're going to be faster than things that are not used very frequently, right? And if the thing is not used very frequently, it basically accumulates into this expensive operation time anyway. So let's actually have several cache implementations. It would be nice to introduce something like cache impl, right? And we're going to have several of these things. So let's define cache none, so we don't have any cache. Now cache LRU, which is going to be 1 in our case, and then we're going to have something like cache Q, right? So this is going to be just a cache Q, and this one is going to be 2, right? So here are our cache implementations, right? So this is going to be cache implementation. If it's equal to cache none, it's going to be that. Otherwise, if cache equal to cache LRU is going to be like this. All of them are LRU, so I didn't think it's a good idea to call it like that, right? Because if you use Q, you also implement an LRU, right? So it's about eviction policy, not about specific implementation. So maybe we're going to call them slightly differently. So this one could be called hash LL, right? So indicating that hash and linked list. Maybe even something like this. This one could be just LL, linked list. So hash LL, and then down there, L if, so it's a implementation, right? L if, just LL. And you know what, it's kind of like, we're going to have huge chunks of different cache implementations, and it's not particularly convenient to like switch between them. What I'm thinking is that we can put different cache implementations in different files. One at cache table 2, basically a lookup table only with no eviction policy. But because we're talking about eviction policy, we're gonna get there. So I'm gonna show the fastest and optimal implementation for this task later. Don't worry about it. Okay, so let's actually put all of that into separate files. So we're gonna have cache none, and this is gonna be a C file, right? So and I'm gonna put it like that, and here we're gonna be just including cache none H. Right, then I can create cache hash LL. This is going to be C, and I'm going to put everything there, like this. So here is a separate file, and then we're going to be just including that file like this, cache hash ll.h. Why? It's the same H, it's actually C file. Cache, yeah, there we go. And we're also going to be including cache llc. So this is just the linked list. Cache ll.c. So in here we're going to be having a node, right? that only contains ptr diff previous, next, then the key and the value, right? So, and the queue is going to be like this. So, and again, we just need to implement 4 operations in here. So I'm going to steal them from hash ll. So it's going to be cache get. So this is the first one. This is going to be the second one. And we also need to have a cleanup. There we go. We need to implement this interface, right? So, cool. So we have a simple queue. And how do we get a value from a queue? We just linearly iterate it, right? So how do we iterate this linked list? Ptr diff I starting from front of the queue, right? We're starting from the front of the queue. I don't remember, I think... Oh shit, this one is actually really dangerous. Yeah, if your list is empty, ll front is gonna suck fault. So we can do something like this. If this is null, we're gonna instantly return false. So yeah, because ll front doesn't really check whether it was already allocated for the first time, so it's like a little bit easier to do it like that. Okay, so then while I is valid, we're gonna be iterating to the next one, q next, right? So we iterated. Okay, if we found the key we're caring about, strcmp key data equals 0. So we are just returning it. So if the user provided a value, we're going to be returning that value from the queue. And now we need to move the node that we found to the beginning, indicating that it was recently used. ll move front, providing the queue, I, there we go, here's the whole thing. We also need to return false. And here we actually return true because we found the element. And here we're going to return false. That's it. That's the simplest possible implementation. You have just a queue, you iterate from left to right, you found the thing, you return this thing, you move that node that you found to the beginning, so the next time you find it faster. Make sense? Is there any questions about this specific implementation? Because this is relatively simple. You just iterate from left to right and then you bring it to the beginning. So yeah, that's pretty much it. So what about cache put? Cache put also going to be super simple. So wait a second. Wait, ll.h ll front. We do check for null in here. Okay, I'm a dummy. Right. So interestingly, if q is null, ll front will return -1, which will automatically stop the loop. Okay, so I forgot how my own library works. Okay, so if I do put, we need to check 2 things. If the count is less than the cache capacity, right? Cache capacity. We're gonna just appending a new thing. So it's gonna be ll push front. We're adding the new thing in here, and then we take the front and setting its key to the key and its value to the value. Cool. So pretty straightforward. Next thing, if we ran out of space, we need to take the back of the queue and move it to the front. ll move front, and we need to repeat this entire thing. Right, so now we're setting it to the front, but since we're repeating, we can actually put it like outside of the loop. And that's it, I think. Yeah, that's pretty much it. So it's actually as straightforward as you can get it. Believe it or not, it is in fact as straightforward as you can get it. So if you have some space, you just push a new node at the front. If you don't have any space, you take the back node and you bring it to the front. So, and then at the front node, you set the key in value, right? If you had some values at the back, they're going to be rewritten by the new value anyway. So that's the whole thing. And also cleanup, right? So in case of cleanup, we just need to free the whole queue. So that's the whole logic in here. All right, so there's something wrong in here. Cache, none, extra tokens. Oh yeah, this one is actually if def. Invalid token. Yeah, so we need to decide what we're gonna use. Okay, so here cache LL. But you know what? I think I also want to add additional thing into the interface of the caches, which sort of prints what is the current cache that we're using, right? So for the none, we can do something like cache name none. For the hash LL, cache name hash table plus linked list, right? Then LL, this one, cache name linked list. Maybe we can even call it just linked list, just for head. And before we go and start implementing everything in here, I'm gonna just print std error. Cache implementation is gonna be, we can just do something like the cache name, and then at the end we're gonna put something like this. So before we start, we actually print what we're doing there. Okay, so if I try to run this entire thing, so cache implementation right now is hash table plus linked list. So this is how it goes, and it's probably printing some stuff. So we'll see how it will perform. So, and then we're gonna compare it to just linked list. 15 seconds. Okay, so maybe we're gonna run it second time because we want to warm up some of the operating system caches, right? Because the hard drive right now is a little busy. We're recording stuff. So yeah, let's actually run the second time. So the second time it could be slightly different. It's actually slower, but anyway. Okay, let's go and try to use the just linked list implementation. Also, it would be nice to have something like error in here, unknown cache implementation, and let's just run it. So just linked list. So we're just using just linked list without optimizing the lookups. So and it is fast. So here's the thing. This is why I don't think this is a very good problem to demonstrate LRU caches. Because the entire data fits into the CPU cache. The entire cache pretty much fits into the L2, L3 CPU cache, and once it's in L2, L3 CPU cache, you can query it however you want. You can do whatever the fuck you want. You can iterate it 10 times over and over again. It's still gonna be fast. That's the problem with the modern CPUs. On the modern CPUs, like they do a lot of magics just to make things go faster. So, and yeah, it's rather interesting, right? I want you to come up with a problem that actually demonstrates LRU, but LRU is just such a really strange thing, right? It's not about going fast. We're measuring the time, right? So, as I already said, LRU is not about going fast. It is not about going fast. It's about going as fast as you can while given the memory limitations. This is very, very important distinction that a lot of people apparently don't realize, and that's why there's a lot of misconceptions and misunderstanding what LRU is. If you don't have a memory limitations, just don't bother. Just put everything into the cache and just forget about it. So situations when you have a memory limitations are actually very, very specific. All right, specific. So where do you have memory limitations? For example, on GPU, right? So you have a limited amount of texture, it's like the size of the texture. And if you build in like an atlas of glyphs or sprites or something like that, you do need LRU cache to evict some of the things from there. And again, another case would be like storing things, like caching web pages in the browser or in a HTTP proxy and stuff like that. So I could probably try to implement like LRU glyph cache or like HTTP proxy, but that is not going to be about LRU cache. There will be a lot of like overwhelming amount of details about computer graphics or about HTTP servers rather than LRU caches. I wanted to come up with a simple example that just lets you focus on LRU instead. But unfortunately, it's kind of difficult to come up with such example given the modern CPUs, right? Yeah, you can just like query it like that and it's gonna be fine. So, but now how, LRU cache aside, how would you even solve such problem as fast as you can? What would be the fastest solution for this specific problem? If we're not limited by using LRU cache stuff thingy. I think the fastest solutions would be to go through the entire document only twice. The first time you collecting the frequency of the words into a hash table without any eviction, just collect everything once. And then on the second pass, you annotate all of the words. Let's try to implement that. How about that? I think we can try to implement that. Let me see. It would be nice to actually fit that solution into our LRU cache thingy, but I'm not sure if we can come up with a good interface for that. Maybe because this is basically requires pre-calculation of some sort. But maybe we can straight up introduce that into the mix, right? We already have a function that cleans up the cache, so maybe we can introduce something that initializes the cache. So cache init, and it will accept maybe the whole content. Why not? Let's accept the whole content, right? And for these caches, it's not going to do anything, right? So for a none, it's not going to do anything. For hash ll, it's also not going to do anything. For ll.c, it's also not going to do anything. And let's create a new cache in here. Cache pre-calc, right? So it's a cache with pre-calculation, right? Which actually does something. So it will accept string view as the content. There we go. So what we're gonna do in here, we're gonna do a single pass over the whole document, right? So I'm gonna take the entire thing. So as we go through the entire document, we don't really care about any of these things. We don't even need any of this shite. Yep, we don't need that. Okay, so we need an item. Right, so this is going to be an item. Oh, okay, we also need to define the name. Pre-calculated hash table. Pre-calculated hash table. So what we're going to store in here, we're going to store the key and the value. That's it. And then we're going to have the table like this. There we go. Cool. So here's the word, and I need to probably first query the word. So I'm going to do mhget table word, and that will return me an index. ptrdiff t index. So if the index is less than 0, that means we don't have that entry in the cache yet. Right, we don't have that entry in the cache yet, so the initial value is going to be 0. Otherwise, the value is going to be equal to whatever we already have in a table. Right, so so can I then automatically just do mhm put, where I would do something like table word value plus 1, and will that work? That's a good question. So did I do init already? I think I need to do something like cache init content. There we go. So here's the cache init, and we need to introduce another thing in here. So this is going to be 3 pre-calc. So this is a pre-calculation effectively. Right, and in the pre-calculation, if cache impl cache pre-calculated, we're gonna include cache precalc C. Alright, so precalc C, so we have everything in here. I just want to try to compile the entire thing just to see what's going on. Okay, so it seems to be compiling. Why do I do that always first try? No, this is not correct. Okay, so it should not... Yeah, so I didn't set the right implementation. There we go, so now it fails. It also will tell me that some of the things are not implemented, like cache get and so on and so forth. Alright, so here's a precalc. So here we initialize the entire thing and everything seems to be compiling. We need to implement the rest of the interface, right? We need to implement the rest of the interface, and so this is going to be the put. This one is... Actually, we need to do get first, I think. Okay. So hm get I table key. Then we have an index in here. If index is less than 0, we return false. Otherwise, we return table index value. Actually, we have to return true if value is available. We return it via this thing. Okay, so this is a get. And put will probably never happen, by the way. Should never happen. Furthermore, we can probably even do something like index is greater than 0. The key should be always available in the cache. Guaranteed. How do you spell guaranteed? Guaranteed. Yeah, my God, so slow. Okay, guaranteed by the cache init. Okay. This one, the cache miss. The cache miss will never happen, guaranteed by cache init. So none of these situations will ever happen because we are pre-calculating the whole cache at once. You see? See what I'm talking about? Right, so if you get, you always get something. If you don't, well, that means we have a bug in this thing. We have a bug in these things. And if you try to put something, that means there was a cache miss. Like all of these things are unreachable. That's why I'm going to be actually, asserting this entire stuff. All right, so everything seems to be, compiling. So semicolon key. So we can also void the key and value. Do we have anything else? Cache cleanup. We didn't implement cache cleanup. Okay, let's quickly implement cache cleanup. So this one is going to be something like this, and then it's going to be hm3. This is going to be the table. Right, so I'm going to recompile. Okay, so now we have pre-calculated hash table. One more time, what are we doing here? We're doing only 2 passes through the entire document, only 2 of them. The first one, basically we're calculating the frequencies of all of the words simultaneously. Right, and putting all of that into the hash table and constantly updating the hash table. That's what we're doing. Right, and then on the second pass, we're just retrieving the values from the pre-calculated cache. Right, and if at any time a cache miss happened, that means we made a mistake in the cache init implementation. All right, so maybe before we go and see the beautiful speed of the pre-calculated cache implementation, we're going to go to just LL and see the speed of that thing first. Right, so I'm going to do run. Something went completely wrong. Excuse me. And oh, it is a pre-calculated cache. Okay, so I forgot to oh my God. Okay, yeah, pre-calculated cache is broken. So I wonder what exactly happened. So it couldn't. Yeah. All right, so I think the problem has happened in the pre-calculation step. We can take a look at it in the cache init thingy. All right, let's go ahead and do that. So it's gonna be no build GDB, right? We're gonna break on cache init, and I'm gonna run the entire thing. Oh, yeah, of course you have to run it with Shakespeare TXT. There we go. Then we're gonna enable this entire thing, and there we go. So we have a content. Okay, so here's the content. Then we have a line. All right, line looks fine. Then original word. Okay, that's also fine. We normalized in the word, so if we take a look and normalize the word, that's fine. We get the index. All right, and the index is -1, so that means the value is going to be 0, and we're incrementing this value. Okay, so if I take a look at the table, right, so the table does contain some things, and yeah, it has a value of 1, which is precisely what I would expect. Okay, so I take the next word, so it's a word orig. This is sonnets, and then I can take a look at that word here as well. I'm querying it, so the index is going to be -1. Right, so the value is going to be something like this, and maybe something wrong happens when we're trying to... Oh, I see. Holy shit. Okay, so I think the problem here is that I forgot to remove some logging in here, right? I forgot to remove some logging. So that should be fine now. Let me try to run this one. There we go. That's it. That's the performance. Chat, are you asleep? I know that a lot of people have left because this is a boring shit for nerds, but so this is a no, well, it's a non-cache. So this is LL. Oh, this one has to be none. Okay. Okay, so linked list. So this is a linked list. 14 seconds. Precalc. That's the speed. I can basically solve it several times per second, actually. Yes. So if you don't use LRU Cache and you pre-calculate the whole thing, that's the whole thing. But we are not using LRU caches. So the moral of the story: nobody knows what is LRU cache, and everyone using word cache and LRU interchangeably without realizing why the fuck do you even need that. It's like it became a really strange buzzword that people throw around without even thinking what it is, and I spent just like 4 hours trying to break it down, and I'm not sure if I actually managed to do that. People will still do that. So yeah, does anyone have any questions? So yeah, I'm gonna actually commit this entire thing. So we're gonna start probably with none, right? Okay. Introduce precalc cache, right? And maybe I should actually put this thing like this. Okay, so here's the thing. You can find everything we implemented today in here if you want to learn about the LRU caches and stuff like that. This entire VOD is going to be available on YouTube, right? So I'm going to upload it to YouTube for anyone who missed it and stuff like that. Does anyone have any questions about like today's stream and what we implemented today? So I think I also want to put the source code into a separate folder. All right. All right, so I'm gonna move this thing. So we remove it. Also remove that stuff. Okay, so if I try to build the entire thing, it's not going to build properly because you're supposed to be building the main.c, so it's going to be src. And now, there we go, it seems to be building. Yep, and we can run, so there's no cache implementation. So yeah, there we go. Does anyone have any questions about today's stream? So here's it is. I demonstrated how to implement LRU Cache using hash table and linked list. Right, we use a hash table from the STB set of libraries, and linked list is my custom linked list implementation. All of that is available here under MIT. You can do whatever you want with this kind of stuff. Feel free to ask me anything. If something not clear, you have an opportunity to ask it right now. I will explain anything. Something unclear. Real world usage? That's a good question. Again, it's when you have a limited amount of memory. Right. For example, like cache for browsers, I think. If I were implementing a browser, right, so I probably would use LRU Cache for that. But in case of a browser, I would work with much bigger data, right? And I would probably store that specific linked list more on a hard drive and hash table to speed up the lookup on the hard drive, right? So it really makes sense for the browser cache, in my opinion, because yeah, you can't cache the whole internet, but you still want to be able to cache the pages, right? And you probably don't want to grow your cache to 1 terabyte, right? So maybe you want to keep the cache around maybe 5 gigabytes, I don't know. So maybe you want to make it customizable. So I would use a cache with some sort of eviction policy. And I think LRU eviction policy would be actually perfect for this kind of stuff. So yeah. So does it answer your question? Kindly explain pre-calc. Okay, I can try to do that. I can even show you how I implement pre-calc, how it works specifically. So here's your Shakespeare, right? So I have a table, right? So I do one pass through the entire document first. Okay, I take the, and I take the and put it into the table and say, okay, it appeared only once. Take sonnets, okay, it appeared once. By appeared once. And so on and so forth, right? Until I encounter by yet again. Okay, so I reached by, all right. After I encountered by, instead of pushing it into the hash table, I just incremented by 1. Right, so then I encounter something like his, right, then I keep track of other things, and then the next time I encounter his, right, I incremented like that. So you see, instead of calculating the frequency of each individual word, I calculate them simultaneously as I go only once through the entire document. I maintain the count for each individual word. And that's how I populate the whole cache. Once I populated the whole cache, I do the second pass where I just annotate each individual word, and I implemented pre-calc just to demonstrate that LRU Cache for this specific problem is not a good idea. It's just I couldn't come up with a better problem to demonstrate LRU Cache because I'm dumb. So, and this pre-calc implementation was a demonstration, was basically a proof of me being a dumbass. So does it explain the situation? Right. I wish I could come up with a good and interesting example that demonstrates an actual usage of LRU Cache really, really well. And also the stream wouldn't take longer than 3 hours. It already did take longer than 3 hours, but I wanted to implement like the whole thing from like ground up almost. Even here I didn't implement it from ground up because I didn't implement linked list and hash tables. But this is the best problem I could come up with, even though it doesn't fit into LRU caches. See what I'm talking about? Did you have something specific in mind for LRU? Not really. I just heard the buzzword and I wanted to see what it's all about. You already explained about it being about limited memory. Yeah. I didn't have any specific in mind, so just people throw this word around without thinking about it, and I just wanted to take a look at it. Are all operations with your linked list is O of 1? I think so. So it doesn't really have that many operations. So let's actually go through all of the operations. So ll.h. So push front is definitely O of 1. Not really. It's O of 1 amortized, I would say. Amortized because it also allocates memory, right? So it does realloc. But it doesn't do realloc very often. It only does realloc when it runs out of capacity, so I would say it's O of 1 amortized. Move front, 100% O of 1. L count, O of 1, because it gets that value from the header, it doesn't go through the entire thing. LL front also from the header, also O of 1. Free, I don't know, it just depends on how the allocator works, but you probably don't do free very often, but I don't know. So it really very much depends on the allocator. It really depends on what you put into LL free macro, right? So by default we use the one from libc, but I only use free at the end of the program, so it doesn't really matter in my opinion. So nothing is clear. I just arrived, but I'll read about it on Wikipedia. Cool. So you can also watch the recording on YouTube channel, right? So you can find the YouTube channel in here. Does anyone have any other questions before I go and stare at my ceiling for 3 hours and then go to bed? Right. Thanks everyone for watching. That's it for the day. That's it for the day. Thanks everyone. Have a good one. And I see you next time, maybe. We'll see. I'll see how it goes. Yeah. So, love you.